Within our solar system are celestial bodies that hold many mysteries. Why does Mars, our twin, have almost no atmosphere and no global magnetic field? Perhaps it never had any? However, the MAVEN satellite launched in 2013 estimated that Mars had indeed experienced a magnetic field comparable to that of the Earth during its first 3.7 billion years of existence. This sudden disappearance of the magnetic field could explain why a large part of the Martian water has also vanished. The case of Pluto has also animated the debate a few years ago. First considered as the 9th planet of the solar system, Pluto is now recognized as a dwarf planet. It is the largest body in this category of stellar objects, ahead of Eris, Ceres, and Makemake, 3 other dwarf planets orbiting around Neptune for the first, in the asteroid belt for the second, and in the Kuiper belt for the third. Yes, our solar system is fascinating, but it is nothing compared to the oddities that are hidden in the immensity of the cosmos. So get ready for an exceptional journey to the farthest reaches of our universe. But beware, on your journey you'll pass by objects whose danger is matched only by their power. You will discover areas that still raise questions for astronomers, passing through places where the laws of physics as we know them no longer apply. This adventure will push us to the limits of the observable universe, 14 billion years old. Are you ready? Your journey into the cosmos begins now. If our universe is about 14 billion years old, you should know that our Milky Way was born almost at the same time. Indeed, scientific research has allowed us to estimate its age by observing the oldest bodies in it. This is the case of the star HE 1523-0901, one of the oldest in our galaxy. Aged 13.2 billion years, this red giant is located at 7,500 light-years from Earth. This news surprised scientists, including the astronomer Anna Frebel and her team, who discovered it in 2007. However, only 6 years later, it was the turn of the star HD 140283 to steal the show. Estimates do not allow to know precisely what is its age. Measurements made with the Hubble satellite led to the conclusion that it could be 14.5 billion years old, which is more than the observable universe. But taking into account the uncertainty of the results and the new measurements bring this estimate between 13.2 and 13.7 billion years. Another fascinating discovery concerning HD 140283 comes to question its origin. In view of its high rotation speed and its location, researchers have put forward a hypothesis. It could be that the star was not formed in the Milky Way, but that it was born in a dwarf galaxy nearby. This dwarf galaxy in question would then have collided with ours to end up devoured, thus offering us part of the stars it housed. However, HD 140283 is no longer the oldest star observed to date. This title belongs to a supermassive star born only 600 million years after the Big Bang. Its name being too complex to be mentioned, astronomers refer to it as the Methuselah star. Located only 200 light-years from our solar system, it is the oldest star we have ever seen. The chances of finding it were slim, But this feat was possible thanks to the pictures taken by the SkyMapper telescope. To estimate its age, scientists based themselves on its iron abundance. Indeed, the telltale sign that the star is so old is the complete absence of any detectable level of iron in the spectrum of the star. Indeed, it took a few million years after the Big Bang for heavier elements such as iron to form in the core of the first stars. The explosion of these stars and supernovae allowed the diffusion of new atoms everywhere in the universe. Thanks to this discovery, we know that the Milky Way is almost as old as the cosmos itself. In the almost 14 billion years of its existence, billions of stars have been born and died in it. The effect of its gravitational force has allowed the creation of complex solar and planetary systems such as ours, systems much closer than we could have hoped. This is the case of Proxima of the Centaurus. If this name rings a bell, it is not without reason. Indeed, Proxima Centauri is the closest star to our Sun ever discovered. But beware, with the technologies we currently have, it is impossible for us to reach it. Let's imagine that you are driving a space shuttle going at a speed of 100 kilometers per hour or 60 miles per hour. To get to Proxima, you would need 60 million years. Now, if you had the possibility to travel at the speed of light, the travel time would be more acceptable, a little more than 4 years only. Located at almost 4.2 light-years from the Sun, it is a small and not very luminous star compared to ours. Proxima is about 8 times less massive and 20,000 times less bright than the Sun. As for its size, it is estimated to be 7 times smaller. It belongs to the category of red dwarfs. Red dwarfs are the most common stars in our galaxy. They represent about 80% of the stars in our galaxy, a total of 240 billion out of the 300 billion stars in our Milky Way galaxy. Even more surprisingly, searches for exoplanets near our own have revealed that 3 relatively massive bodies orbit our small neighbor. These planets are respectively named Proxima B, C, and D. Unfortunately, these new worlds do not seem to be ideal candidates for the emergence of life as we know it. Due to its strong and unstable magnetic field, solar flares are frequent on Proxima Centauri. Thus, although Proxima B is located in the habitable zone of its star, the chances of it harboring life forms remain slim. Another surprising feature of Proxima Centauri is its relationship with 2 other nearby stars. These double stars are called Alpha Centauri A and B, and together with Proxima Alpha Centauri C, they form an unusual star system. Not far from Earth, there are other planetary systems just as incredible, fueling beliefs of extraterrestrial life. If you're a science fiction fan, you may be familiar with the series Babylon 5. In this show, the eponymous space station is located in the Epsilon Eridani system. But this system was not invented for the purposes of the script. It does exist. Located at 10.5 light-years from us, the orange dwarf in its center is the 10th closest star to us. More massive and bright than red dwarfs, these stars remain less imposing than yellow dwarfs such as our Sun. According to astronomers' estimates, the star is 800 million years old. It is therefore a newborn, among the wonders of the cosmos. This star gives us a glimpse of what our Sun was like after only a few million years of existence. But that's not all. After observation, astronomers have revealed the existence of a remarkable exoplanet. A gas giant, 1.5 times more massive than our Jupiter, and located at about 3.5 astronomical units from its star. That is, 3.5 times further away than the Earth is from the Sun. Between the star and its planet is a belt of dust, asteroids, and other cosmic debris. The same is true outside the planet's orbit. This second belt would shelter colder bodies such as comets. This particular arrangement is not unlike that of our own solar system. Between Mars and Jupiter is a ring of low-mass bodies called the asteroid belt. And outside the orbit of Neptune, we find the famous Kuiper belt, populated by comets. If the Epsilon Eridani system interests scientists so much, it is because it gives us a good overview of what our solar system may have been at the beginning of its formation. Currently, research continues in order to detect other planets that have escaped the measurements of astronomers. If our Milky Way is home to many red dwarfs, orange dwarfs, and other yellow dwarfs, it also has much more impressive stars. Bodies with phenomenal dimensions, constantly growing, until they swallow the planets that have the misfortune to be near them. These stars are called red giants. Some are visible from Earth, and are sometimes the source of myths about constellations. This is the case of Arcturus. Observable from the northern hemisphere of our globe, it is the brightest star in the constellation of the Cattleman. If its mass is equivalent to that of the Sun, its luminosity is 300 times greater. But how did Arcturus get there? Well, the star has consumed all the hydrogen contained in its center to attack the outer layers. It is then that nuclear fusion reactions started, consuming helium for the synthesis of heavier elements. Because of these reactions, the star has gained in volume, but it has lost in density and temperature. Since then, its radiation tends towards the red, hence its name. At the end of the combustion process, the red giant will give way to a huge cloud of gas with a white dwarf at its center. You know these clouds as planetary nebulae. You should know that a similar fate awaits our Sun in about 4 to 5 billion years. By observing our sky, astronomers have counted more than 1,000 white dwarfs in our galaxy. But some estimates suggest that there are several tens of billions. Let's get back to Arcturus. In addition to its enormous size, this star is intriguing because of its orbit. Located in the so-called Milky Way halo, it moves on a very inclined plane, unlike most other stars. It is therefore not centered on the disk of the Milky Way like our Sun. At present, we know that about 30 stars orbit on this particular plane. Together they form the Arcturus group. One reason for this unusual behavior is that the stars in this group are believed to have come from another galaxy that collided with ours 5 billion years ago. In any case, Arcturus will no longer be visible to the naked eye within a few 100,000 years. If Arcturus is a big star, it is nothing compared to VY Canis Majoris, a red hypergiant located in the constellation of Canis Major, about 3,900 light-years from Earth. It is considered one of the largest known stars in the observable universe, but it is also the largest star in our galaxy. The latest estimates indicate a monstrous size, 2,200 times that of our Sun. If it took the place of our Sun in our solar system, it would extend between the orbits of Jupiter and Saturn. Next to it, our Sun, so huge in our eyes, would be only a speck of dust. VY Canis Majoris is also very bright. It emits about 400,000 times more light than the Sun. However, even giants are not eternal, and this hypermassive star is dying, little by little. Being very unstable, it loses huge amounts of matter, second after second. Thus, its lifespan should not exceed more than 1 million years. Within 100,000 years, VY Canis Majoris will explode into a gigantic supernova. Yes, VY Canis Majoris has a terrifying scale. But lurking in the cosmos, even more massive stars radiate throughout the observable universe. Such is the case with R136A1, a massive star located in the Tarantula Nebula. In this region of the cosmos, stars grow like mushrooms on the edge of country roads. This star nursery is located in the Large Magellanic Cloud, a dwarf galaxy very close to the Milky Way, behind the Great Dog and Sagittarius. Just as the Moon is a satellite of the Earth, we can say that these galaxy embryos are satellites of our Milky Way. R136A1 is thus to date the most massive star known in our universe. Its mass is estimated at 230 times that of the Sun, also emitting 5 million times more light. Thus, if we were to compare our Sun to this star, it would not be brighter than the full moon. This unprecedented brightness indicates that the star is losing mind-boggling amounts of matter at every moment. Thus, taking this data in reverse, it is estimated that R136A1 must have weighed at its birth 320 times the mass of the Sun. A record as fascinating as terrifying, breaking our beliefs about the maximum size of stars at the time of its discovery. But like VY Canis Majoris, its lifespan will be short. This giant among giants will probably not shine for more than 4 million years. On the scale of the universe, this represents only a blink of an eye. When it reaches the end of its life, it could explode in a cosmic fireworks display of enormous proportions, a supernova. Fortunately, hypermassive stars are few and far between in our galaxy. However, there are celestial objects even rarer and more dangerous than these molten giants. Objects so massive that nothing can escape, neither matter nor light. These are, of course, black holes. It has been known for several years that most galaxies have a hypermassive black hole in their center. Ours is no exception. In 2002, a group of astronomers used high-resolution observations made with the Keck telescope and the VLT to detect this cosmic abyss. By observing the motion of stars in the center of our galaxy, they found that some of them were undergoing abnormal accelerations. This could only mean one thing: an invisible object with an incredible force of gravity must be nearby. This discovery was a direct proof of the existence of supermassive black holes. the hypothesis had already been formulated by Albert Einstein at the beginning of the 20th century, following his work on relativity. However, the Austrian genius did not believe in the existence of such objects. To understand how Einstein's theories predicted the existence of black holes, we need to look at a physical datum called libration velocity. This value tells us how fast a body must travel to get out of the gravitational field of a star whose mass and radius are known. By pushing the reasoning, we understand that for a star of extreme density, the libration speed is higher than the speed of light. However, the theory of general relativity tells us that this speed is a universal constant and that nothing can exceed it. It is therefore assumed that for a star with a very small radius compared to its mass, it would be able to swallow light. This is how the hypothesis of black holes was put forward. Today, their existence is accepted, and research continues to decipher their mysteries. Indeed, our current understanding of black holes is limited. We know that these celestial objects are extremely massive and compact. Their gravitational force is so strong that nothing, not even photons, can resist their attraction. Some of them are formed when supermassive stars die. The heart of the latter collapses on itself in a cataclysmic event, bringing into play prodigious forces. This is how stellar black holes come into existence. But stellar black holes, although impressive, pale in comparison to their cousins. If the mass of a stellar black hole, born in the ashes of a star, can reach 10 to 20 times that of the Sun, it is nothing compared to the 40 billion solar masses that supermassive black holes can have. Sagittarius A, located 27,000 light-years from Earth, is the black hole at the center of our galaxy. With a mass of about 4 million times that of the Sun, our star appears tiny. And yet, next to these monsters of the cosmos, even our galactic black hole, although immense, can hardly compete. M87, of its name, would have a mass equivalent to 6.5 billion times that of the Sun. Thus, M87 would have a mass 600 times greater than Sagittarius A. But how did these giants that inhabit the middle of most galaxies come into existence? This question is very much debated by the scientific community at the moment. Some believe that they were originally stellar black holes that evolved by accretion of matter over several billion years. However, many researchers reject this hypothesis. For this, they argue that there is not enough matter available near the black holes to ensure such expansion. Thus, others believe that these chasms were formed during the first moments of our universe, when it was much hotter and denser. Perhaps we will know more in the next few years. Another fascinating thing about black holes is what is called the event horizon. This is a region around the black hole from which gravity is so strong that it becomes impossible to escape its attraction. This boundary thus separates the observable world from the heart of the abyss, allowing us only to make assumptions about its nature. It is not a physical limit, like a wall or a barrier, but a zone of space from which everything that falls inside is ineluctably swallowed up. Beyond this point, the laws of physics as described by the theory of relativity no longer apply. However, if you were able to pass the event horizon and survive your journey, it is likely that your body would undergo a phenomenon of spaghettification. This strange term designates a phenomenon that is much less so. On Earth, gravity is strong enough to hold us down. However, it is not strong enough for a difference in attraction to be felt between our head and our feet. However, this is precisely what would happen if you were to get too close to a black hole. The simple distance between your upper and lower body would be strong enough to stretch your body like a long string. Moreover, at the horizon of the black hole, it is considered that space and time become infinite. One of the feats of the genius Albert Einstein is to have demonstrated that space, like time, are nested dimensions that can be bent. Thus, the incredible density of black holes bends space and dilates time in a spectacular way. As you move closer to their center, you would see time passing slower and slower until it almost stops at the horizon. It is difficult to imagine what lies at the heart of them. Our current understanding of things leads us to think that a singularity is hidden there. This singularity designates a point of infinite density, causing a curvature of space-time, also infinite. As you can imagine, this image does not please scientists. They are therefore trying to unravel the mystery of the heart of black holes by appealing to the various theories of quantum mechanics. Unfortunately, no satisfactory conclusion has been found so far. Nevertheless, our observations of black holes have revealed something quite surprising. We were just explaining that nothing, not even light, can escape from a black hole. Light is an electromagnetic wave, so black holes cannot emit radiation. And yet, a genius scientist managed to demonstrate the opposite in 1974. His name is Stephen Hawking. He proved that black holes do emit radiation, and that this is an integral part of their nature. Although this radiation is undetectable with the current means because extremely weak, several experiments confirm its existence. To explain this paradox, we must once again turn to quantum mechanics. Thanks to it, Hawking was able to demonstrate that black holes do emit a radiation, now called Hawking's radiation. This is a thermal radiation caused by quantum fluctuations in the space-time around the black hole. These variations would lead to the creation of virtual particles separated into two groups. The first part would be absorbed by the black hole, while the other would escape from it, thus generating the famous radiation. If black holes have not yet revealed all their mysteries, they nevertheless remain objects of fascination that are conducive to the emergence of many theories. Interdimensional portals, origin of the Big Bang, glass holes, gateway to the multiverse. One thing is sure, these spatial abysses have not finished making talk about them. Our galaxy is home to many things that arouse our curiosity. It alone contains between 200 and 400 billion stars, but also between 100 and 200 billion exoplanets. So we are still in the early stages of discovery. Nevertheless, we also know that the Milky Way is only a drop of water in an ocean of other galaxies of various sizes and shapes. The observable universe would contain 2,000 billion of them. This inordinate number is enough to make one dizzy. And yet, the observable universe would represent only a dust. Indeed, the entire universe could contain 13 million times the observable universe. With so many bodies in the universe, it would be logical to think that at least one of them would contain a form of life, such as it exists on Earth. Some even believe that life could be much more diverse than we can imagine. It is possible that within our own galaxy, there are tens of thousands of planetary systems with primitive and complex life forms, extraterrestrials with reason, capable of thinking and interacting in complex societies. Unfortunately, there is no direct evidence that life exists anywhere but on Earth. But if life is potentially so abundant in the cosmos, how can we explain that we have never come across at least one living creature outside our planet? This question, which obsesses astrobiologists as much as amateur astronomers, is known as Fermi's paradox. Enrico Fermi is an American physicist of Italian origin who, among other things, worked on nuclear physics during the first half of the 20th century. Winner of the Nobel Prize in Physics in 1938, he was also interested in the question of the number of planets in the universe. After making estimates, he concluded that the probability that we are the only life form in the universe was ridiculously low. He then asked the question: if there were extraterrestrial civilizations, their representatives should already be with us. Where are they then? This sums up Fermi's paradox quite well. In response to this question, many scientists have put forward hypotheses. One of the most commonly accepted is that the distances separating the planets of the same galaxy are such that it would be impossible to cover them. Even traveling at the speed of light, it would take too long, especially when we know that our galaxy is about 100,000 light-years in diameter. Others also put forward the problem that resources are too limited to colonize other planets by traveling through space. Even if we progressed by colonizing planets in succession, many of them would be too inhospitable or too poor in certain materials to serve as staging points for such an expansion. Finally, some think that a form of life capable of traveling rapidly from planet to planet would have no interest in coming to Earth to meet us. For these beings coming from elsewhere, we would not be more evolved than simple bacteria. But it is human nature to dream. Our thirst for knowledge feeds a burning desire to meet people from another world. Thus, even if the probability that the human species will one day encounter extraterrestrials is low, we will always look for their presence at the edge of the universe. If we haven't discovered alien counterparts despite all our research, there are stranger, but also more dangerous things that scientists have observed while scanning the cosmos. Terrifying discoveries, such as the existence of black holes and other phenomena of cataclysmic proportions. As explained earlier, the death of some massive stars can give rise to stellar black holes. But sometimes things happen differently, giving rise to a much more spectacular event, a supernova. Supernovae are very violent stellar explosions that occur at the end of the life of a massive star. There are two types, Type 1a supernovae and Type 2 supernovae. Type 1a supernovae occur when a neutron star accretes too much matter around it, often from a neighboring star. This gain of matter continues until it triggers a nuclear fusion chain reaction that causes the star to explode. These explosions are extremely bright and all give off about the same luminosity. This constant allows scientists to measure their distance quite accurately. Type II supernovae are formed when the core of a massive star collapses under its own weight, triggering an explosion that destroys the star. Type II supernovae are even more luminous than Type Ia supernovae, but the amount of light they give off varies considerably from one explosion to another. These cosmic booms are uniquely violent events. Fortunately, the chances that we will ever be affected by one of them are slim. Although they occur every 3 seconds in the observable universe, they are rarer in the Milky Way. It is estimated that the frequency is in the order of 1 to 3 every 100 years. It is also important to understand that under their destructive appearance, supernovae play a crucial role in the evolution of the universe. By expelling matter over incredible distances, they allow the propagation of heavy elements, thus serving for the creation of new stars and planets. As the astrophysicist Hubert Reeves said, "We are all stardust, because the atoms that make up our bodies and the world around us come from stars that died billions of years ago." For as long as we have known that supernovae exist, none have been observed in our Milky Way. However, such a phenomenon would have occurred near us in the year 1604. SN 1604, of its scientific name, is better known as Kepler's supernova. This one remained visible in the skies for more than a year before gradually disappearing. The German astronomer Johann Kepler thought he had just observed the appearance of a new star. He detailed this unprecedented phenomenon in a book entitled On the New Star in the Foot of Ophiuchus. Since then, no other explosion of this kind has been observed directly in our Milky Way. However, it is very likely that it has happened since. The second closest supernova that we have seen is called SN 1987A. Its light reached the Earth on February 23, 1987, and was observed only a few hours later by professional and amateur astronomers. It occurred in a nearby galaxy, the Large Magellanic Cloud, located more than 160,000 light-years away. According to recent analyses, it is probably a Type II supernova, produced by the death of a red supergiant. The study of the latter has allowed us to learn more about the death of stars and the way they propagate matter through the cosmos. Moreover, some elements from this explosion have reached us. This is the case of neutrinos, elementary subatomic particles of very low mass that hardly interact with matter. SN 1987 allowed us to prove their existence, advancing research on particle physics. Thus, even such distant events can inform our local understanding of the world. It is also fascinating to see how such a large explosion finally leads us to discoveries on the subatomic scale. Even if supernovae are very interesting, it is not recommended to get too close to them. Just like black holes, they bring into play considerable forces with disastrous consequences. For example, Type II supernovae, which are the most powerful but also the rarest, emit a luminosity equivalent to 10 billion times that of the Sun. To put it another way, the explosion of a single star can shine brighter than the entire galaxy that hosts it. This is notably the case of the supernova SN 1999 EM. Located 25 million light-years from Earth, its light in the visible range is currently equivalent to 200 million times that of the Sun. All this is impressive, even terrifying, but it is nothing compared to hypernovae. These particular explosions are hotter, brighter, and even more destructive. We speak of hypernova when the explosion is of the order of 100 supernovae. The power released is then 10 to the 46th power joules. The Tsar Bomba, the most powerful nuclear bomb ever exploded, only released 10 to the 17th power joules. It was therefore about 100,000 billion times less powerful. To put it another way, if our nuclear bombs had the force of a flick of the wrist, hypernovae would be as powerful as a kilo of TNT. In this very specific category of cosmic explosions, there is one that absolutely outclasses all others. It is the most powerful supernova ever detected. Its name is ASASSN-15lh. This is literally a cosmic assassin whose magnitude exceeds the limits of our imagination. The scientists behind its discovery explain that ASASSN-15lh is the most powerful supernova ever discovered in human history. The source of the power of the explosion and the energy released remains a mystery, since no theory of physics can really explain it. And for good reason. When the intensity of the explosion was at its peak, this hypernova shone 20 times brighter than all the stars in our galaxy combined. Faced with this discovery, scientists were left speechless. How could a phenomenon of such magnitude have occurred? And yet, they still managed to observe the hypernova, even though it is located 3.8 billion light-years away. All the analyses have come to the conclusion that the light spectrum of this formidable blast does not resemble at all that of other previously studied supernovae. In particular, they tell us that the original star must have been poor in hydrogen, which is not the case for most of the stars around us. One theory is that ASASSN-15lh is the consequence of the explosion of a particularly rare type of neutron star, a magnet star. Also called a magnetar, it would be a rotating star with a rotation speed of 1,000 revolutions per second, converting all the energy of its rotation into light. Other scientists put forward another theory to explain the extreme characteristics of ASASSN-15lh. It is known that most of the observed supernovae are found in faint and small galaxies. This is a sign of their genesis and intense activity. Stars form and die more quickly. The hypernova occurred in a galaxy even larger and more luminous than our Milky Way. The second hypothesis is that it is not a star explosion, but an unusual phenomenon near a black hole of extreme mass. In any case, the studies around this mystery continue. Let's hope that it will lead us to other fabulous discoveries in the years to come. If Type II supernovae are the result of the collapse of a massive star, Type Ia supernovae work differently. For these explosions to occur, the presence of a neutron star is necessary. But what exactly is a neutron star? In fact, neutron stars are very compact and dense celestial objects that form when massive stars end their life cycle. Lighter stars would become white dwarfs, while heavier stars could form stellar black holes. these giants would eventually collapse under their own gravity, causing an extreme compression of matter. This compression is such that the two elementary particles, protons and electrons, end up fusing to form neutrons. This nuclear fusion produces a lot of energy, which prevents the total collapse of the star, creating a stable neutron star. Neutron stars have diameters of a few kilometers, but a mass comparable to that of the Sun. If you could buy a 1-liter bottle containing the same volume of a neutron star, the mass of that bottle would be about 1,000 billion tons. That's about the weight of all the things produced by all of humanity. From clothes to packaging, roads, dots, and skyscrapers. This incredible density produces extremely strong gravitational fields, which can reach millions of times the Earth's gravity. It is also important to know that neutron stars are not very bright, at least in the visible spectrum, because they do emit light, but it is mainly X-rays and gamma rays. Like supernovae and black holes, there are several kinds of neutron stars. They are mainly grouped in two categories. On the one hand, we have pulsars, and on the other hand, neutron stars that produce gamma-ray bursts. The pulsars emit bursts of X-rays or gamma rays at regular intervals. We could compare them to a kind of cosmic sonar. Discovered for the first time in 1967 by Jocelyn Bell and Anthony Hewish, they have recently been used to demonstrate the existence of gravitational waves. A particular type of wave, and very difficult to detect, subjecting matter to the laws of gravitation. Their existence had been predicted by Einstein's relativity, but it was only proven in 2016, following the collision of a binary system of two black holes. This cosmic event of massive magnitude generated waves strong enough to be detected on Earth, despite the 1.3 billion light-years that separated them from us. It was also the first direct evidence of the existence of black holes. But let's get back to our pulsars. At present, we have been able to detect about 3,000 of them, mainly in our galaxy and in our close neighbors. The reason pulsars emit such regular waves is that these dense bodies rotate on themselves at an extreme speed. Their rotation period varies between a few milliseconds and a few seconds. This period of rotation is given to us by the nature of the waves they emit. Radio waves for the slowest, and X-rays or gamma rays for the fastest. As for pulsars producing gamma ray bursts, it is not one, but two bodies. These two pulsars orbit each other at high speed, forming a binary system. When they collide, they also create a wave of gravitational waves that can be detected from Earth. A gamma-ray burst is certainly one of the most violent phenomena that occur in the cosmos. Like supernovae, this shock generates a luminosity that can reach billions of times that of the Sun. Sometimes gamma-ray bursts are associated with very high-frequency radio waves. These are called FRBs. These are short-lived emissions of intense electromagnetic radiation of extragalactic origin. FRBs are considered to be very rare and enigmatic phenomena, with only about 100 events detected to date. During our journey, we have seen that the universe is full of intriguing objects. At any given moment, events of unprecedented power are taking place, and uncontrollable forces are at work. Black holes are a good example. If these objects, by their nature, are already mysterious, there is a particular type even stranger. They are called quasars. This is an acronym for quasi-stellar radio sources. They are celestial artifacts, very bright and very distant, which are found in the heart of some galaxies. These galaxies are called active because their center produces a luminosity that nothing, not even supernovae, equals in the cosmos. The most likely theory is that quasars result from a large accretion of matter around a supermassive black hole. Particles such as hydrogen or helium are thus strongly accelerated under the effect of gravitation. This high speed gives them such energy that they produce a strong electromagnetic radiation of a blinding brightness. Let's take the example of the quasar 3C273. Discovered with the help of photos taken by the famous Hubble Telescope, it is located about 2.4 billion light-years from our galaxy. Its prodigious luminosity exceeds 1,000 billion times that of the Sun. This represents as much light as 1,000 times all the stars in our galaxy combined. Thus, 3C273 is one of the brightest objects ever observed. Today, probability calculations suggest that there are about 100 billion quasars in the cosmos. Since the quasars are all located at cosmological distances, i.e. several billion light-years, this tells us something about the nature of our own universe. Indeed, if the universe was static and unchanged since its creation, we should observe these prodigious sources of light near us. But this is not the case. The vast majority of them are located in the outer reaches of the observable universe. This discovery is therefore a strong argument in favor of the Big Bang theory. The light that reaches us from quasars is in fact an after-mirage of the formation of galaxies several billion years ago, shortly after the Big Bang. It thus informs us about the formation of the universe as we know it, but also about the genesis of our own Milky Way. Since it also contains a supermassive black hole, it is likely that a quasar was there at the beginning of its formation. Another theory, a little more unusual, tries to explain the incredible luminosity that results from quasars. According to this theory, quasars are in fact white holes, the opposite of black holes. Instead of absorbing matter, white holes would eject huge amounts of it at a very high speed. This jet of accelerated matter would produce the characteristic light of quasars. But for this hypothesis to be valid, it requires believing in the existence of wormholes, bridges between points in space-time that would allow instantaneous travel from one place to another in the universe. Wormholes would then be found at the center of some black holes and would emerge at the heart of white holes, explaining why the latter reject so much matter. Unfortunately, wormholes remain hypothetical objects, like many others in the bestiary of relativity. But a recent discovery could put everything in question. At the end of 2022, scientists from the University of Caltech in California worked on a quantum computer, that is to say, a computer whose operation is based on the laws of quantum mechanics and particle physics. They have succeeded in creating a miniature wormhole within the Sycamore quantum processor developed by Google. They observed that two distinct groups of particles were connected through a tunnel, causing a particle to instantly migrate from one group to the other. Today, this feat of science is still being studied, but it could well represent a further step in the reconciliation of quantum mechanics with the theory of general relativity. To date, these two models make it possible to explain the laws of physics at the scale of the infinitely small and the infinitely large, respectively. However, a deep incompatibility exists between these two approaches, which scientists are trying to bring together. We have just traveled to quasars, objects that shine billions of light years away. This stopover allowed us to understand that in its infancy, our universe was very active. Galaxies were emerging here and there, gradually filling the void and gathering matter around them. This process of creation gave birth to clusters of forms as diverse as intriguing. If we know that the Milky Way, like Andromeda, is a spiral galaxy, observations of the sky show us that this is not the case for all our neighbors. Indeed, some of them take much more incongruous contours. Spiral galaxies have a flattened disk shape in which spiral arms wrap around a central nucleus. Generally, this core is a supermassive black hole. Rich in gas and dust, the activity within them is strong, so that many stars die and are created at any time. There are also elliptical galaxies. As their name suggests, these have an ellipsoidal shape, similar to a rugby ball. They are generally poorer in gas and stellar dust. Their activity is therefore less. We can say that they are, in a way, galaxies at the end of their life. Even more surprising, the barred spiral galaxies form a flat disk, crossed by a central bar of matter. This is notably the case of the Dwingaloo 1 galaxy, located in the constellation of Cassiopeia. There are several types of barred spiral galaxies, and according to the classifications, ours is also one. Let's also mention the lenticular galaxies, which form a flat disk surrounded by a spherical central nucleus. These galaxies have no spiral arms. The disk of matter surrounding their nucleus is uniform. To make an analogy, we can say that the heart of these galaxies would be like a planet surrounded by a ring of matter, like Saturn. This matter is mainly dust, so that we observe very little star formation. Some argue that these galaxies were once spiral galaxies, but that today they have consumed all their gas and star formation. However, because of their high luminosity, others believe that they are the product of the merger of two galaxies, giving them a large mass, free of spiral arms. There are many types of galaxies in the cosmos, and classifications by shape are not absolute. Some even straddle two distinct shapes, probably because of a galactic merger. This sometimes leads to strange mixtures. We have, for example, galaxies in tidal tail. For these, a bridge of matter is created between two galaxies so that they never merge completely. They thus present two nuclei that leave behind them long trails of matter, forming huge tidal tails. This is the case of the spectacular Antennae galaxy. As for the Cartwheel galaxy, it would be the result of the collision of two galaxies, one very large and the other much smaller. The small galaxy would have crossed the larger one in its center and perpendicular to its disk, giving rise to an incredible nesting. Speaking of nesting, it happens that two galaxies never merge completely until they form a very particular cosmic architecture. This is the case of the ARP-143 system, a triangular-shaped structure containing two galaxies in constant interaction. Sometimes it happens that under the effect of gravitation, many spirals of matter are grouped together, forming what is called a cluster. The most famous representative is undoubtedly the Virgo cluster. Located at about 60 million light-years from us, it would contain more than 1,500 galaxies, all within a radius of only 7 million light-years. This is approximately 132 times the diameter of our Milky Way. As you can see, if only in their shape, galaxies are fascinating. This is even more true for the curiosities they contain. But the most curious thing about them is that they are not visible. In fact, we don't even know if this thing is real. It is commonly called dark matter. In the late 1970s, an American astronomer named Vera Rubin became interested in the motions of stars within galaxies. She knew from Newton's laws of motion that bodies orbiting a central point have a slower period of revolution as they move away from it. This is the case for Uranus and Neptune, whose speed of rotation around the Sun is much lower than that of Venus and Mercury. Within a galaxy, the same phenomenon should occur. The more the stars are in the periphery, the more their speed should be slowed down. However, Vera Rubin notes that from a certain point, the speed of stars ends up stagnating as one moves away from the center, instead of constantly decreasing. This unexpected behavior poses a problem of understanding. The most likely hypothesis is that somewhere, lurking in the darkness of the cosmos, there must be a mass of unknown nature, allowing the stars to maintain their speed. It is called dark matter. It would then have the very specific property of not emitting or reflecting light, and of interacting weakly with the other known forms of matter. Its effect would be solely gravitational, thus explaining the structures and movements within galaxies. It is estimated that it makes up 80% of our universe. In other words, this means that we would only be able to understand 20% of our universe, and that within this 20%, many things like black holes still escape our understanding. If we accept the dark matter hypothesis, most of our universe would be hidden from our view. At first, scientists thought that this lack of matter was due to the presence of black holes, exoplanets, brown dwarfs, and neutron stars that we had not yet observed. But after the discovery of fossil radiation, that is, the reminiscences of the first photons emitted in the observable universe, this idea was invalidated. Indeed, the fossil radiation allows us to determine quite accurately the amount of matter known in the universe. And this amount would be far from being sufficient to replace the hypothetical dark matter. At present, the most promising candidates to explain the nature of dark matter are the WIMPs. This stands for Weakly Interacting Massive Particles. Massive particles that interact weakly with ordinary matter. But again, the problem is repeated. If WIMPs do exist, their nature is completely unknown to us. In particle physics, a hypothesis called supersymmetry gives us some answers. For this hypothesis to be valid, it predicts the existence of a bestiary of particles never before observed. One of the goals of the experiments conducted at the CERN particle gas pedal is to find these mysterious elements. If supersymmetric particles are favored by some researchers, it is because they are also a key factor in string theory. This complex theory of particle physics mainly tells us that subatomic elements are in fact made of one-dimensional objects, close to the infinitely small, called strings. It is important to note that currently, no observation has validated the hypothesis of the string theory or dark matter. In addition, some argue that dark matter simply does not exist. The problem would in fact come from the theories that we use, namely the theory of general relativity. Relativity would explain only a part of the physics that governs our world, but it would be incomplete, just like Newtonian mechanics in its time. Still, dark matter does not only explain the structure of galaxies and clusters, it is often associated with its counterpart, dark energy. Also called dark energy, it is another hypothesis explaining the expansion of the universe. To understand it, we must keep in mind that the universe is constantly expanding. On an astronomical scale, all galaxies are moving away from each other. To illustrate this phenomenon with an image, imagine a dotted grid drawn on a balloon. Now imagine blowing up the balloon again and again. You would then see the dots move away from each other as the space expands. In this simplistic example, we are in 2 dimensions, but in the universe, the same phenomenon occurs in all 3 dimensions of space. More surprisingly, the expansion accelerates more and more for galaxies located at the limits of the observable universe. It is to date the only phenomenon whose speed exceeds that of light. Dark energy would therefore be one of the forces explaining this phenomenon of incomprehensible expansion. By taking it into account, we are able to determine the real size of our universe. We know from the fossil record that the universe is about 13.8 billion light-years long. But because the expansion is exceeding the speed of light, photons emitted by even more distant objects have not yet reached us. If we could capture them, we would be able to see the universe in its current state and size. It would measure not 13.8 billion light-years, but 46 billion light-years. An absolutely immeasurable size, which for us is similar to infinity. All this raises even deeper questions. If the universe is expanding, what is it expanding into? Is there another universe with well-defined borders surrounding ours? Or are there simply no boundaries? And if the universe is expanding, what will happen when all the galaxies are separated from each other by billions of light-years? We may never get answers to these questions, but one thing is for sure: we will never stop asking them. We are almost at the end of our interstellar journey, but before we leave, let's take the time to observe some more fascinating discoveries. We talked earlier about the shapes of galaxies, but what about their size? Well, if you turn to the constellation Virgo, you can observe the largest galaxy known to date. IC 1101 is 600 million light-years away and is 6 million light-years across. Compared to it, our Milky Way, barely 100,000 light-years wide, seems ridiculously small. Within it, there are no less than 100,000 billion stars, 250 times more than in the Milky Way, with a total mass estimated at 100,000 billion times that of the Sun. This is quite simply gigantic. It is possible that IC 1101 is the result of successive mergers between several galaxies, but nothing is certain about it. Where things get really dizzying is when you consider that even more monstrous galaxies probably exist, but they have simply never been discovered. IC 1101 is the largest known galaxy, but it is by no means the most distant. This title goes to HD 1. Its distance? 13.5 billion light-years from Earth. Because of its distance, the images that reach us from it show it in a completely new light. Indeed, we are witnessing the beginning of its formation when it was only 300 million years after the Big Bang. To hope to see it, we must look in the direction of the Big Dipper. Since it is still in its infancy, from our perspective, it is a small galaxy. It is only 6,000 light-years long, which makes it ridiculously small compared to IC 1101. But this youth also makes it more active. According to the images we have of it, it produces about 20 times more stars per unit area than the Milky Way. If a few hundred years ago we were still struggling to detect distant stars in our own solar system, like Neptune or Pluto, it is incredible to see how much our ability to scan the cosmos has evolved. Let's hope that the discoveries will continue for many years to come. In the meantime, we can already marvel at what the sky gives us to observe on summer nights. During our journey through the cosmos, we have discovered many artifacts, each more surprising than the other. Between red giants, red dwarfs, and neutron stars, we know that not all stars are as warm as our sun. Even worse, they can give rise to violent events, such as the formation of stellar black holes and supernova explosions. But they can also end their days peacefully, letting their gases dissipate, and giving the universe the necessary material for the formation of new glowing stars. We have also seen that black holes hold many mysteries. They can form quasars or produce a phenomenal amount of gravitational waves when they collide. They are also an excellent source of imagination for science fiction. It is curious to note that even though the term asteroid is over 200 years old, it has not yet been formally defined by the International Astronomical Union or any other scientific organization. Previously, the term minor planets was used as a synonym for the word asteroid. However, after the International Astronomical Union first defined the term planet in 2006, the term minor planet was officially withdrawn, and it was replaced by the category small bodies of the solar system, which includes all irregularly shaped bodies that revolve around the Sun and are not planets, dwarf planets, or their moons. At the 2006 International Astronomical Union meeting, another important event took place. Ceres was reclassified as a dwarf planet. Thus, from a formal point of view, the largest asteroid in the solar system became Vesta. Although the word asteroid still has no official definition in astronomy, it generally refers to small bodies in the solar system that are not comets, i.e., they do not exhibit cometary activity in the form of coma and tail formation. But there is an important nuance to consider. Many comets have long since lost their volatile reserves, so it is quite difficult to distinguish them from asteroids. Often, these burned comets give more elongated orbits, but this is not always the case. There are several options for classifying asteroids. Depending on the orbital characteristics, they are combined into groups and families. Usually, the group is named after the first asteroid discovered in a given orbit. Groups are relatively loose formations, while families are denser, resulting from the destruction of large asteroids due to their collision with other objects. Another criterion can be used to classify asteroids, that based on their chemical composition and reflective surface characteristics or albedo. In the most simplified form, there are three main types of asteroids: carbonaceous, which have a very dark surface, silicate, and metallized. The first two categories represent about 75% and 17% of the total number of known asteroids, respectively. Recently, asteroids have had their own international celebration. In 2016, the United Nations General Assembly proclaimed June 30th as International Asteroid Day. The date was not chosen by chance. On June 30th, 1908, a celestial body exploded over Siberia. This incident, known as the Tunguska event, is still the subject of scientific debate about the nature of this celestial object. Today, on this International Day, events are held around the world to inform the public about the danger of asteroids and possible methods to prevent asteroid collisions with the Earth. Half of the mass of the asteroid belt belongs to four objects: Ceres, Vesta, Pallas, and Hygiene. The total mass of the asteroid belt is about 4% of that of the Moon. Ceres is the only object in the asteroid belt large enough to be classified as a dwarf planet. It has a diameter of about 950 kilometers, or 590 miles, while Vesta, Pallas, and Hygiene have an average diameter of less than 600 kilometers, or 370 miles. The majority of the other bodies are the size of a dust particle. More than 200 asteroids are known to exceed 100 kilometers, or 60 miles, and a study at infrared wavelengths has shown that the asteroid belt contains between 700,000 and 1.7 million asteroids, with a diameter of 1 kilometer or more. The temperature of the asteroid belt depends on the distance of its objects from the Sun. For dust particles within the belt, typical temperatures range from minus 73 degrees Celsius, or minus 99 degrees Fahrenheit, at 2.2 astronomical units, to as low as minus 108 degrees Celsius, or minus 162 degrees Fahrenheit, at 3.2 astronomical units. However, due to rotation, the surface temperature of an asteroid can change by solar radiation. Most asteroids in the asteroid belt have an orbital eccentricity of less than 0.4 of an inclination of less than 30 degrees. The orbital distribution of asteroids peaks at an eccentricity of about 0.07 and an inclination less than 4 degrees. Thus, although a typical asteroid has a relatively circular orbit and lies in the plane of the ecliptic, some asteroid objects can be very eccentric or extend well beyond the plane of the ecliptic. Sometimes the term main belt is used only to refer to the most compact central region. Thus, the limits are between the strong Kirkwood deviations between 2.06 and 3.27 astronomical units, and at orbital eccentricities lower than about 0.33, as well as at orbital inclinations lower than about 20 degrees. In 2006, this central region represents 93% of the minor objects discovered and numbered in the solar system. The astronomical database that lists the small bodies of the solar system, JPL Small Body, mentions more than 700,000 known asteroids of the main belt. The distribution of asteroids along the semi-major axis of their orbits is not random, as it has discontinuities called Kirkwood gaps. These are areas of the belt devoid of asteroids. Indeed, the orbit of asteroids present in these areas is not stable over long periods because of the effects of orbital resonances with Jupiter. The semi-major axis of an asteroid is used to describe its orbital period around the Sun, and its value determines its revolution. In 1866, Daniel Kirkwood announced the discovery of gaps in the distances of orbiting bodies from the Sun. These are located in places where their period of revolution around the Sun was part of the orbital period of Jupiter. When the mean orbital period of the asteroid is a partial orbital period of Jupiter, a mean motion resonance with the gas giant is created, sufficient to bring the asteroid into new orbital elements. As a result, the orbits progressively move into different random orbits with a larger or smaller half-axis, either initially due to the motion of Jupiter's orbit or due to disturbances or preliminary collisions. The central region of the asteroid belt is sometimes subdivided into 3 zones based on the largest Kirkwood gaps. Zone 1 extends from the 4:1 resonance to the 3:1 resonance, i.e., from 2.06 to 2.5 astronomical units. Zone 2 extends from the end of Zone 1 to the 5:2 resonance, i.e., around 2.82 astronomical units. Zone 3 starts at the outer limit of Zone 2 up to the 2:1 resonance gap, which corresponds to 3.28 astronomical units. The high population of the asteroid belt creates a very active environment, where asteroid collisions occur frequently on astronomical timescales. A collision between major belt bodies with an average radius of 10 kilometers or 6 miles is expected to occur about once every 10 million years. The collisions may break the asteroid into several smaller pieces, leading to the formation of a new asteroid family. Conversely, collisions occurring at low speeds can, on the contrary, link 2 asteroids. Thus, in several hundred million years, the asteroid belt will no longer look like the one we know today. In addition to the asteroid bodies, the asteroid belt also contains dust bands whose particle size can reach several hundred micrometers. This material is formed, at least in part, as a result of collisions between asteroids and collisions of micrometeorites with asteroids. Due to the Poynting-Robertson effect, the pressure of solar radiation causes a slow spiral of this dust towards the Sun. The combination of this fine asteroid dust with the ejected cometary material produces the zodiacal light. This faint glow can be seen at night in the direction of the Sun, along the plane of the ecliptic. Asteroid particles emitting visible zodiacal light have an average radius of about 40 micrometers. The typical lifetime of particles in the main zodiacal clouds of the belt is about 700,000 years. Thus, in order to maintain the dust, new particles must be constantly produced within the asteroid belt. It was once thought that asteroid collisions were the main component of the zodiacal light. However, computer simulations have attributed 85% of the zodiacal light dust to fragments of Jupiter-like comets, rather than to comets and collisions between asteroids in the asteroid belt. Asteroids in the asteroid belt are classified according to their spectra, most of which fall into 3 main groups: C-type or carbonaceous asteroids, S-type rich or silicate asteroids, and M-type or metallic asteroids. The C-type or carbonaceous asteroids are, as their name indicates, rich in carbon. They dominate the outer regions of the asteroid belt. Together, they represent more than 75% of the visible asteroids. They are redder than other asteroids and have a very low albedo. Their albedo varies from 0.03 to 0.1, which means that they reflect only 3 to 10% of the incident light. Because of this, C-class asteroids are difficult to detect, so in reality, their share of the main belt may be well over 75%. Their surface composition is similar to that of carbonaceous chondrite meteorites. In chemical composition, their spectra correspond to the original composition of the primitive solar system, with the disappearance of the only lighter and volatile elements. In addition to carbon, these celestial bodies contain water, so they can be detected with observations in the infrared range. The largest asteroid of this class is Hygiene, whose diameter is estimated at 434 kilometers, or 270 miles. S-type asteroids rich in silicate, i.e. ordinary rocks, are more frequent in the inner region of the belt, within 2.5 astronomical units of the Sun. The spectra of their surfaces show the presence of silicates and some metals, but do not contain significant carbon compounds. This indicates that their materials have been considerably modified from their original composition, probably by fusion and transformation. They have a relatively high albedo that varies between 0.1 and 0.22. This category represents about 17% of the total asteroid population. The metal-rich M-type asteroids represent about 8% of the total population. They are mostly located in the center of the main belt. Their spectra resemble those of iron-nickel. It is thought that some of them were formed from the metallic cores of primitive bodies, differentiated and destroyed by the collision. The albedo of metallic asteroids is between 0.1 and 0.19, i.e., they have moderate reflectivity. It should be noted that scientists are not sure that metallic asteroids are made of metals because they are too thin. This means that either M-class asteroids have a similar composition to asteroids of other classes, or there are many cavities in their internal structure. However, there are also silicate compounds that can have a similar appearance. For example, the large M-type asteroid 22 Calliope does not appear to be composed primarily of metal. Within the asteroid belt, the distribution of M-type asteroids peaks at the semi-major axis, around 2.7 astronomical units. It is not yet clear whether all M-types have a similar composition, or whether this is a label for several varieties that do not fit into the main C and S classes. There are other rarer classes, classes B, E, P, A, D, etc. Sometimes an asteroid cannot be strictly assigned to a single class. It is then considered to be of mixed type, which is indicated by two letters, for example, CG. One of the mysteries of the asteroid belt is the relative rarity of V-type asteroids that exhibit the properties of basaltic chondrites. Theories of asteroid formation predict that objects the size of Vesta or larger should form crusts and mantles that would be composed primarily of basaltic rocks, so that more than half of all asteroids should be composed of basalt or olivine. Yet observations show that 99% of the predicted basaltic material is missing. Until 2001, it was thought that most basaltic bodies found in the asteroid belt came from the asteroid Vesta, hence the name V-type. However, the discovery of asteroid 1459 Magnaya in 1937 showed that the chemical composition is somewhat different from other basaltic asteroids discovered until then. This hypothesis was reinforced by the new discovery in 2007 of two asteroids in the outer belt, 7472 Kumakari in 1992 and 10537 1991 RY16 in 1991, with different basaltic compositions that could not have come from Vesta. These last two are the only V-type asteroids found in the outer belt to date. Most of the asteroids are relatively small in size. In total, about 30 asteroids larger than 200 kilometers or 125 miles in diameter have been discovered. The largest objects in the asteroid belt are Ceres with 946 kilometers or 588 miles in diameter, Vesta with 525 kilometers or 325 miles in diameter, Pallas with 513 kilometers or 320 miles in diameter, and the asteroid Hygiene with a diameter of 434 kilometers or 270 miles. These four celestial bodies represent about half of the mass of the entire main belt. With Ceres considered as a dwarf planet, Vesta is thus the largest asteroid of the main belt. Moreover, Ceres is the only body in the asteroid belt large enough to maintain a spherical shape. Most asteroids are potato-shaped, although some take a more unusual shape. This is the case of asteroid 216 Cleopatra, which looks like a dog bone. Contrary to its representation in science fiction movies, the asteroid belt is quite spacious. It is so vast that the average distance between two asteroids is about 1 million kilometers or 600,000 miles. Thus, the probability of a spacecraft colliding with an asteroid is virtually zero. The material in the belt is so well distributed that many self-propelled spacecraft have passed through the belt without incident. However, collisions between large asteroids do occur and can lead to the formation of a family of asteroids whose members have different orbital characteristics and composition. In addition, the asteroids of the main belt are unevenly distributed. There are areas in which they are virtually absent. These areas, called Kirkwood gaps, are cleared of asteroids by the gravitational influence of Jupiter. On the other hand, some common bodies in the outer belt show cometary activity. Since their orbits cannot be explained by the capture of classical comets, it is thought that many other asteroids may be icy, sometimes sublimating, due to small impacts. The asteroid belt was discovered gradually during the 19th century. However, the area between Mars and Jupiter attracted the attention of astronomers long before that, with the aim of searching for a planet. The German astronomer Johann Kepler noticed in 1596 deviations in the orbits of Mars and Jupiter. He thought that there was too much deviation in these orbits, and he explained this by the presence of a planet in this region. Today, scientists explain these deviations as a result of the gravity of asteroids. In 1766, another German astrophysicist, Johann Daniel Titius, noticed an apparent pattern in the arrangement of the planets. He found a formula by which it was possible to calculate the approximate position of all the planets in the solar system. The principle of this formula was that the ordinal distance of the planets from the Sun increases exponentially according to the following hypothesis. Counting from the center of the solar system, each succeeding planet will be located about twice as far away as the planet before it. According to this hypothesis, known today as Titius-Bode's Law, there must have been an as-yet unknown planet between the orbits of Mars and Jupiter. In 1781, when William Herschel discovered Uranus, the orbit of the planet was almost exactly right according to the Titius-Bode Law, which convinced many scientists of the truth of the law of interplanetary distance, and led astronomers to conclude that there must be a planet between the orbits of Mars and Jupiter. It was on January 1, 1801, that Italian astronomer Giuseppe Piazzi discovered the first asteroid, Ceres, in this region of the solar system. From this discovery, scientists believe that Ceres was the famous lost planet. Soon, other similar objects were discovered in the same region of the solar system. As scientists discovered more and more celestial bodies between Mars and Jupiter at an increasing rate, it became more and more difficult to count them as planets. Thus, these bodies were removed from the list of planets, and Herschel's choice of nomenclature, i.e. asteroids, gradually came into effect. One interesting fact put the Titius-Bode Law in check. When Neptune was discovered in 1846, it turned out that its location did not match Titius's predictions. Apparently, the Titius-Bode Law is nothing more than a mathematical coincidence, and not a physical law at all. To this day, there is no scientific explanation for this law, and according to astronomers, it is a coincidence. In 1868, about 100 asteroids were discovered, and an astrophotograph by the German astronomer Max Wolf was made later. A total of 1,000 asteroids were discovered in 1921, 10,000 in 1981, and 100,000 in 2000. Modern asteroid exploration systems currently use automated means to discover new asteroids and minor planets in ever-increasing numbers. The asteroid belt has been of interest to scientists not only in past centuries but also in recent years. Since the 1970s, several spacecraft have been able to reach the asteroid belt and study its objects. The first achievement of modern technology in the study of this cluster of celestial objects was the flight of the American space probe Pioneer 10, designed to study Jupiter, which entered the region on 16 July 1972. This spacecraft was the first to cross the asteroid belt. Since then, 9 other spacecraft have crossed the belt. At the time, it was feared that debris in the belt could pose a danger to a spacecraft, but 12 spacecraft have since crossed without incident. The Pioneer 11, Voyager 1 and 2, and Ulysses spacecraft have crossed the belt without obtaining images of asteroids. Other missions, including Galileo, Near-Shoemaker, Cassini, New Horizons, and Rosetta, have photographed some asteroids. The Galileo spacecraft was the first spacecraft to take pictures of asteroids. It studied the S-type asteroids 951 Gaspra in 1991 and 243 Ida in 1993, and discovered for the first time an asteroidal moon of 1.4 kilometers in diameter, orbiting the asteroid 243 Ida. The space probe Near-Shoemaker was launched in 1996, and in February 2000, it entered the orbit of asteroid 433 Eros. Thus, it was possible to study in detail its chemical composition, as well as to build a three-dimensional model of a celestial body. In 2001, the probe landed on Eros and explored for 2 weeks its soil, to a depth of 10 centimeters. Once these images were obtained, NASA decided that any spacecraft flying near the asteroid belt should try to take pictures of these objects. In 2003, the Japanese probe Hayabusa was launched. It explored the asteroid 25143, Itokawa. The device was able to collect soil samples from this asteroid and send them to Earth. The Dawn mission was the first to visit the asteroids Vesta in 2011 and Ceres in 2015. Thanks to this mission, nearly 69,000 photographs of these asteroids and many other data were obtained. On the other hand, on its way to Jupiter, the Juno spacecraft crossed the asteroid belt without collecting scientific data. Because of the low density of material in the belt, the chance of a probe colliding with an asteroid is now estimated to be less than 1 in 1 billion. Most images of asteroids in the belt have been obtained from brief flybys by probes aimed at other targets. Only the Dawn, near Shoemaker, and Hayabusa missions have studied asteroids for extended periods in orbit and on the surface. NASA's Psyche spacecraft is scheduled to launch in October 2023. It is scheduled to set out to discover asteroid 16 Psyche. Scientists suggest that this asteroid is composed of a core of iron, nickel, and gold. Initially, scientists thought that the asteroid belt was formed as a result of the destruction of a hypothetical large planet, which according to the Titius-Bode Law should have been orbiting between Mars and Jupiter. The planet was named Phaeton, after the son of the ancient Greek sun god Helios. However, calculations simulating the destruction process of Phaeton did not confirm this hypothesis. It should be noted that many astrophysicists around the world supported the hypothesis of the collapsed planet until the end of the 20th century. In fact, the amount of energy required to destroy a planet, coupled with the combined mass of the asteroid belt, which is only about 4% of the mass of our Moon, as well as the major chemical differences between the asteroids, does not support this hypothesis. In 2018, a study by scientists at the University of Florida found that the asteroid belt was created from the remains of several protoplanets, not a single planet. This research supports the hypothesis that the asteroid belt was formed about 4.6 billion years ago from the primordial solar nebula by small clumps of cosmic dust called planetesimals, the smallest precursors of protoplanets, which form during the accretion process. Over several million years, the accretion process caused small particles to stick together and gradually increase in size. When the clusters reached a sufficient mass, they could attract bodies by gravitational attraction and become planetesimals. Some of these planetesimal bodies eventually became the planets we know today. At the dawn of the asteroid belt's formation, the planetesimals were too disrupted by Jupiter's gravity to form a planet. Instead, they continued to orbit the Sun as before, colliding from time to time. In regions where the average impact rate was high, planetesimal destruction tended to outweigh accretion, preventing the formation of planet-sized bodies. In fact, orbital resonances were activated when the period of an object in the belt was part of the orbital period of Jupiter, placing the object in a different orbit. The region between the orbits of Mars and Jupiter creates many of these orbital resonances. Thus, the orbits of asteroids are violently perturbed whenever their period of revolution around the Sun forms an orbital resonance with Jupiter. At these orbital distances, a Kirkwood gap occurs when they move to other orbits. Recall that the Kirkwood gap represents the deviation in the distribution of the semi-major axes, or orbital periods of the orbits of the main belt asteroids. They correspond to the locations of the orbital resonances with Jupiter. In the region of the solar system between Mars and Jupiter, the gravital perturbations of Jupiter have endowed the planetesimals with too much orbital energy to be captured and agglomerated to form a planet, dynamically exciting these bodies and increasing their velocity relative to each other. The collisions became too violent, and instead of merging, the planetesimals and most of the protoplanets were reduced to small pieces. In the early days of the Earth's existence, asteroids underwent some degree of melting. Some asteroids may even have experienced periods of explosive volcanism and emitted magma. Nevertheless, because of their relatively small size, the melting period was necessarily short, compared to much larger planets, and generally ended within the first tens of millions of years of the solar system's formation. In August 2007, the study of zircon crystals in an Antarctic meteorite, believed to have come from Vesta, showed that it, and by extension the rest of the belt, formed quite rapidly, within 10 million years of the formation of the solar system. The current asteroid belt is thought to contain only a small fraction of the mass of the original belt. Computer simulations suggest that the primary asteroid belt could have had a mass equivalent to that of the Earth. Primarily due to gravitational disturbances, most of the material was ejected from the belt during the first million years of its formation, leaving less than 0.1% of its original mass. As a result, 99.9% of the original mass of the asteroid belt was lost during the first million years of the solar system's history. Some of the fragments ended up in the inner solar system, causing meteorite impacts on the inner planets. Since the formation of the belt, the size of the asteroids has remained relatively stable. They have not increased or decreased significantly. The 4-to-1 orbital resonance with Jupiter, at 2.06 astronomical units from the Sun, can be considered the inner limit of the asteroid belt. Jupiter's perturbations send deviating bodies into unstable orbits there. Most of the bodies formed within the radius of this space were captured by Mars, which has an aphelion of 1.67 astronomical units, or rejected by its gravitational disturbances early in the history of the solar system. When the asteroid belt first formed, the temperature at a distance of 2.7 astronomical units from the Sun formed a snow line below the freezing point of water. Therefore, planetesimals formed outside this radius were able to accumulate ice. In 2006, a group of researchers reported that a population of comets had been discovered in the asteroid belt beyond the ice line, which may have provided water to Earth's oceans. According to some models, the outgassing of water during the formation of the Earth was not sufficient to form the oceans. An external source, such as cometary bombardment, would have been necessary. Scientists have drawn attention to the heterogeneity of the composition of the asteroid belt. The silicate-type asteroids, similar in their properties and composition to the terrestrial planets, are located in the inner ring, and the carbon-type asteroids, on the contrary, approaching the composition of giant planets, are in the outer ring. According to astrophysicists, this may indicate that asteroids were formed as debris during the genesis of other planets, after which they were projected into the region between Mars and Jupiter, where they are currently located. To confirm the proposed hypothesis, the scientists simulated the process of planet formation from a disk of gas and dust, and verified the possibility of planet formation from debris that migrates to the giant planets and concentrates in a certain area. The formation of each of the 4 planets was modeled separately, taking into account the gravitational influence of Jupiter and Saturn with a corresponding orbital resonance. By gathering all the data, the scientists received information about the possible distribution of silicate asteroids, and after further studying the growth mechanism of gas giants, the scientists came to the conclusion that gas accretion could lead to destabilization of their orbits and subsequent ejection of carbon-like asteroids into a region closer to the Sun. Based on the data obtained, the scientists estimated the inclination and eccentricity of the resulting fragments' orbits and came to the conclusion that the mechanism they proposed could indeed lead to the formation of the asteroid belt in its modern form. Thus, most likely, the asteroid belt immediately formed in its present, rather sparse form, with a small mass and a heterogeneous compositional distribution. The ability to simulate the process of planet formation is leading to the emergence of new hypotheses about the origin of objects in the solar system. For example, scientists have recently proposed a new scenario for the formation of Mars, which probably formed right at the current location of the asteroid belt. Today, scientists know that the asteroid belt is by no means a broken planet, but that it formed from the remnants of protoplanetary material that appeared at the origin of the solar system. Ceres is the largest object in the main asteroid belt that lies between the orbits of Mars and Jupiter. With a diameter of 946 kilometers or 588 miles, Ceres is both the largest asteroid and the only dwarf planet in the asteroid belt. Ceres was the first asteroid discovered by Giuseppe Piazzi at the Palermo Astronomical Observatory on January 1, 1801. It was originally thought to be a planet, but was reclassified as an asteroid in the 1850s after the discovery of many other objects in similar orbits. The International Astronomical Union decided in 2006 to classify Ceres as a dwarf planet, alongside its primary status as an asteroid. Ceres is a surviving protoplanet, a sort of planetary embryo, formed 4.56 billion years ago. The only one preserved in the inner solar system, while the others have either merged to form telluric planets, broken up, or have been ejected from the solar system by Jupiter. Ceres formed as a centaur, a small body in the solar system, with either a perihelion or a semi-major axis between those of the outer planets, most likely between the orbits of Jupiter and Saturn, and was scattered in the asteroid belt when Jupiter migrated slightly inward from the solar system. Ceres follows an orbit between Mars and Jupiter, inside the asteroid belt and closer to the orbit of Mars, with an orbital period of 4.6 Earth years. Ceres is an orbital resonance of mean motion, close to 1:1, with the asteroid Pallas. But a real resonance between them is unlikely, because of their small masses compared to the large distances between the asteroids. Such relationships are rare. The rotation period of Ceres is 9 hours and 4 minutes. It has an axial tilt of 4 degrees. This is low enough that Ceres' polar regions contain permanently shaded craters, which should act as cold traps and accumulate water ice over time, as on the Moon and Mercury. Ceres is the only object in the asteroid belt that is surrounded by its own gravity, although Vesta and perhaps other asteroids have been in the past. Even at maximum brightness, it is too faint to be seen with the naked eye, except under extremely dark skies. Ceres has been classified as a C-type asteroid, and due to the presence of clay minerals as a G-type asteroid. Ceres represents about 1/3 of the total estimated mass of the asteroid belt, or 1.3% of the mass of the Moon. Its surface area is about the same as that of India. Modeling has shown that Ceres may have a small metallic core, due to the partial differentiation of its stony fraction. The surface of Ceres is homogeneous and rich in carbonates and ammoniacal phyllosilicates altered by water. The ocean of water thought to have existed early in Ceres' history must have left a layer of ice beneath the surface when it froze. The fact that the Dawn spacecraft found no evidence of such a layer suggests that Ceres' original crust was at least partially eroded by later impacts, carefully mixing ice with salts and ancient silicate-rich seafloor material below. Ceres' surface is hot enough for the surface ice to sublime. The sublimation material could explain Ceres' dark surface compared to icy moons in the outer solar system. Studies by the Hubble Space Telescope indicate that graphite, sulfur, and sulfur dioxide are present on the surface of Ceres. The former is obviously the result of cosmic weathering of Ceres' ancient surfaces. The latter two are volatile and should either escape quickly or be deposited in cold traps, and are apparently associated with areas of recent geologic activity. Scientists have identified 22 ancient cryovolcanoes on Ceres, ranging from 16 to 86 kilometers, or 10 to 53 miles wide, and 1.1 to 4.4 kilometers, or 0.6 to 2.8 miles high. Cryovolcanoes form about once every 50 million years. In August 2020, NASA confirmed that Ceres is a water-rich body with a deep reservoir of brine, which leaks to the surface in various places, causing bright spots. There are indications that Ceres has a thin atmosphere of water vapor emanating from the water ice on the surface, making it an active asteroid. Surface water ice is unstable at distances less than 5 astronomical units from the Sun, so it should turn to vapor if exposed to direct solar radiation. Water ice can migrate from deep layers of Ceres to the surface, but it will then evaporate in a very short time. On January 22, 2014, ESA scientists reported for the first time the discovery of several sources of water vapor at mid-latitudes. The exploration was carried out using the space observatory Herschel. This was unexpected because large bodies in the asteroid belt do not normally emit vapor, which is a characteristic of comets. Possible mechanisms for vapor release are sublimation from exposed surface ice or cryovolcanic eruptions resulting from internal heat or increased pressure in the subsurface layers of the ocean due to the growth of overlying layers of ice. In 2017, Dawn confirmed that Ceres has a transient atmosphere that appears to be related to solar activity. The ice on Ceres can sublimate when energetic particles from the Sun strike the ice inside the craters. Although the hypothesis of a potential microbial home for extraterrestrial life is not discussed as much as for Mars, Europa, Enceladus, or Titan, there is evidence that the icy mantle of Ceres was once a watery subsurface ocean. It appears to contain up to 20% carbon by mass in its near surface. Indeed, carbon-rich compounds are intimately mixed with the products of rock-water interactions such as clays and can create conditions favorable for organic chemistry. This is the largest asteroid in the belt. Its average diameter is 525 kilometers or 326 miles, and its mass is estimated at 9% of the mass of the main belt. It is the only asteroid that can be observed without a telescope or binoculars, as it reflects 42% of the sunlight. Vesta's orbit crosses the interior of the belt. It is located in the main Kirkwood Gap. The orbital period of the asteroid Vesta around the Sun is 3.6 years. This asteroid has a rather important asymmetry. If its shape were more spherical, then Vesta could be classified as a dwarf planet. Unlike many other asteroids, a complex geological history is visible here. The core is composed of nickel and iron, while the mantle is composed of rocks. Over time, the core and mantle have melted and crystallized. These phenomena have resulted in a large amount of minerals. The current distance between the asteroid Vesta and the Sun is 2.2 astronomical units. The rotation of the asteroid around its axis is 5.3 hours, and the axis is tilted by 29 degrees. Although temperatures on Vesta fluctuate throughout the year, the model predicts that the average annual temperature near Vesta's north and south poles is less than -128 degrees Celsius, or -198 degrees Fahrenheit. Near Vesta's equator, however, the average annual temperature is about -123 degrees Celsius, or -189 degrees Fahrenheit. It is assumed that many of the small objects surrounding the asteroid are parts of Vesta that have broken off as a result of collision with other planets. This asteroid has a huge crater near its south pole. It was formed in a collision that created a whole family of asteroids moving near it. Pallas was the second object discovered in the asteroid belt. It represents 7% of the mass of the main belt, with an estimated diameter of 513 kilometers or 320 miles. In terms of both size and mass, Pallas ranks third among the main belt objects, just behind Ceres and Vesta. In 2006, Pallas was considered a candidate for the title of dwarf planet, but due to its shape, which is too different from the spherical shape, astronomers consider it unequivocally as an asteroid. Pallas moves in an elliptical orbit around the Sun, so the distance between these two bodies is not constant. The minimum distance between this asteroid and the Sun is 2.1 astronomical units, while the maximum distance is 3.4 astronomical units. In addition, the revolution of Pallas around the Sun lasts 4.6 Earth years. The orbit has a large inclination to the plane of the ecliptic, which is 34.8 degrees. For other large asteroids, this inclination is less than 10 degrees. The asteroid also rotates on its own axis, making a revolution every 7.8 hours. The average speed of Pallas on its orbit is 17.6 kilometers per second, or 11 miles per second. There is a 1-to-1 resonance between Pallas and the dwarf planet Ceres. This means that their periods of revolution around the Sun coincide. The albedo of Pallas, i.e. the proportion of reflected light, is 15%. Such reflectivity, as well as its large size, make Pallas one of the brightest objects in the asteroid belt, but it cannot be seen with the naked eye. According to its spectrum, Pallas belongs to the carbon group asteroids, or C group. This means that Pallas is dominated by anhydrous silicates, sulfides, and magnetides. It also contains polymers. The asteroids of this class have a bluish spectrum, and they almost do not absorb light with a wavelength below 500 nanometers. There is a whole family of Pallas, that is to say, a group of asteroids which are probably fragments formed during the collision of Pallas with another celestial body. All the asteroids of this family belong to the same class, and their orbits are distinguished by a strong inclination. But none of these asteroids is a moon of Pallas. Little is known about the relief of Pallas today, since it is studied only with telescopes. Near the equator is a crater that was formed more than 1.7 billion years ago during a collision with a meteorite with a diameter of 40 kilometers or 25 miles. Due to the steep inclination of the orbit, greater than 34 degrees, Pallas is very difficult to explore with spacecraft. However, in 2024, the launch of the mission Psyche is planned, within which an auxiliary flight of the probe Athena towards Pallas is possible. It is the fourth largest asteroid, with an estimated diameter of 434 kilometers or 270 miles, and the 10th object discovered in the asteroid belt. For a long time, Hygiea was thought to have an irregular shape. Only observations in 2017 showed that in fact, the asteroid's shape is close to spherical. This means that one day, Hygiea could be recognized as a dwarf planet. It represents 3% of the mass of the entire belt. The average surface temperature of Hygiea is minus 109 degrees Celsius, or minus 164 degrees Fahrenheit. It is an asteroid with an albedo of 0.07, so its surface is very dark, reflecting only 7% of the sunlight that falls on it. The darkness of Hygiea's surface is due to the fact that it belongs to the so-called C-class asteroids, in which carbon predominates. Moreover, Hygiea is the largest representative of this class. The chemical composition of these asteroids is close to that of the chondrite meteorites, which fall most often on the Earth. It is also assumed that the protoplanetary cloud had approximately the same composition, from which the planets of the solar system were formed 4.5 billion years ago. Hygiea, like the other asteroids, has an elliptical orbit. The maximum distance between this asteroid and the Sun is 3.5 astronomical units, while the minimum distance is 2.77 astronomical units. Hygiea takes 5.5 years to complete one revolution around the Sun. The orbit of the asteroid has a slight inclination to the plane of the ecliptic, equal to only 3.8 degrees. It is only in 2018 that scientists have managed to estimate the period of revolution of Hygiea around its own axis. It is equal to 13.8 hours. In his case, the direction of rotation could not be determined reliably. Calculations show that the orbit of Hygiea is unstable, so it will change chaotically due to the effect of the gravity of Jupiter and Saturn on the asteroid. It also has its own family of asteroids formed by the collision of Hygiea with another celestial object. Computer simulations show that during this collision, Hygiea was completely destroyed, but over time, most of the fragments reconnected to each other under the influence of gravity. It is not surprising that asteroids can collide with the Earth, and if this had not happened very often in the past, we probably would not exist today, because most of the water on our planet came from asteroids and comets. Planets form from a large disk of gas and dust. The inner regions of this disk are close to the star and are usually very hot. Water and other volatile substances evaporate from them. Thus, the disk appears to be dry inside, and it is in these inner regions that Earth-like planets form. So by default, there should be relatively little water. The same thing happened with our Earth. The water or water vapor involved in its formation slowly rose to the surface over time as a result of volcanism. But this was clearly not enough. Most asteroids form behind the so-called ice line. The ice line is an isothermal line that represents the limit beyond which it is cold enough for water in the form of ice to be part of the celestial bodies that form from the protoplanetary disk. In our solar system, the ice line crosses the asteroid belt between the orbits of Mars and Jupiter. This is why most asteroids contain a lot of frozen water. These asteroids often collided with the Earth in ancient geological times. This is how a large amount of water arrived on our planet. But asteroids could bring not only water, but also something more. Some scientists suspect that perhaps the first complex molecules, the first building blocks of life, arrived on Earth carried by asteroids. And it could even be argued that asteroid impacts, such as the one that occurred 66 million years ago, notably extinguishing the non-avian dinosaur kingdom, spurred evolution and forced it to take a new direction. Without the collision that took place 66 million years ago, mammals, and therefore humans, would certainly not have become the dominant class on this planet. Therefore, it is fair to say that asteroids are an important factor in the emergence of terrestrial life. The presence of this asteroid belt in the inner solar system is closely associated with Jupiter. This gas giant grew faster than any other planet during its formation, and eventually became the largest planet in the solar system. Because of its large size, Jupiter's gravitational disturbances could have prevented the formation of a planet in its vicinity. This is why there are no other large celestial bodies between Mars and Jupiter, only asteroids. If Jupiter had formed farther from the Sun, the asteroid belt would have been farther away as well, like the Kuiper belt, and the asteroids would have had little chance of colliding with the Earth. If Jupiter had been closer to the Sun, the region would have been warmer, and the asteroids would not have contained ice. Another very interesting fact is the motion of Jupiter around the Sun. In fact, its path of motion has been constantly changing. Astronomers call this phase of the solar system's development planetary migration. When Jupiter migrated, it slightly touched the asteroid belt. Thus, many asteroids were expelled from the solar system, or were destroyed. This event has its importance, since it signs the beginning of the Great Late Bombardment. Its estimated duration is 50 to 150 million years, centered on 3.9 billion years. The rate of bombardment is estimated to be 20,000 times that currently observed on Earth, which corresponds, for example, to an impact of an object of more than 1 kilometer every 20 years, allowing a water supply. Thus we see that the solar system needed not only a large planet that forms in the right place, beyond the ice line, but also a planet that could migrate in the right direction. Astronomers don't yet know enough details about other planetary systems to know if the situation there is similar to ours, but the current data are not very encouraging. However, scientists have the opportunity to analyze the available data and find out how many large exoplanets are in front of or behind their ice lines. Recently, research has shown that most exoplanets are not in the position needed to create the right asteroid belt. But the importance of these research results should not be exaggerated, since we are talking about planets close to their star that are not easy to detect. It is only when astronomers discover many more extrasolar planets that it will be possible to be more affirmative. And here again, the problem of migration arises. It was already difficult enough to establish the exact nature of migration in our solar system. This is even more difficult to do with extrasolar planetary systems. However, if we want to study the dynamics of planetary motion with sufficient precision, we must look into this question. It is very interesting to observe how complex the interactions of the components of the planetary system can be. Small rocks, interplanetary dust particles, comets, and everything else also play an important role. All the bodies influence each other, and all of them have allowed life to appear on our planet. Many craters on the surface of the Moon, Mercury, and other solar system bodies are often used to illustrate the danger that asteroids represent for the Earth. However, it should be remembered that the vast majority of these craters were formed during the late bombardment period. On the surface of the Earth, thanks to modern technologies, including the analysis of satellite images, it is possible to detect traces of collisions with asteroids, which belong to much later periods in the evolution of the solar system. The largest and oldest known crater is the Vredefort Dome, which is located in South Africa. Its diameter is about 250 kilometers or 155 miles. Its age is estimated at 2 billion years. The Chicxulub crater on the coast of the Yucatan Peninsula in Mexico was formed after an asteroid impact 66 million years ago, equivalent to the energy of an explosion of 100 teratons of TNT. With a period of high volcanic activity, this event signed the famous extinction of the non-avian dinosaurs, causing tsunamis, earthquakes, and climate changes due to the layer of dust formed in the atmosphere that obscured the sun. One of the most recent craters is the meteor crater from a large iron asteroid of 30 to 50 meters in diameter that hit the Colorado Plateau in northern Arizona with a mass of several 100,000 tons 49,000 years ago. In total, there are now about 170 impact craters formed by falling celestial bodies. The event near Chelyabinsk in Siberia attracted the most attention when on February 15, 2013, an asteroid entered the atmosphere in this area, which was estimated to be about 17 meters or 55 feet in size and 13,000 tons in mass. It exploded in the air at an altitude of 20 kilometers or 12 miles, its largest part weighing 600 kilograms, or 370 miles, fell into Lake Chebarkul. The energy of the explosion was equivalent to 0.5 megatons of TNT, which corresponds to 30 bombs dropped on Hiroshima. The Chelyabinsk asteroid became the most detailed event of this magnitude after the explosion of the Tunguska meteorite on June 30, 1908. According to modern estimates, the fall of celestial bodies, such as Chelyabinsk, in the world occurs about once every 100 years. As for the Tunguska event, trees were burned over an area with a diameter of 50 kilometers or 30 miles. Such disasters occur about once every 300 years. When we arrive in the star system K2-18, more than 100 light-years away from where you are now, we will observe its star and the 2 exoplanets discovered so far that orbit it. We will focus on K2-18b, an exoplanet that looks very promising as a second Earth, and we will find out what life might be like on this strange planet, if indeed there is alien life on this second Earth, located thousands of billions of kilometers away from us. Are you ready to explore the K2-18 star system, which may be home to an Earth-like exoplanet? We are now leaving our planet for this solar system located 124 light-years away. Get ready, it will be a long journey. Let's take advantage of this journey through the stars to observe some beautiful objects in the universe relatively close to us. The closest star system to ours has been named by astronomers Alpha Centauri. We are only 4.3 light-years away from Earth. Originally, Alpha Centauri was organized around a double star, the stellar couple Alpha Centauri AB. These two stars were named by astronomers Alpha Centauri A, or Rigil Kentaurus, and Alpha Centauri B, Ptolemaeon. Today, what you have in front of you is a triple system, because the stellar pair captured the star Proxima Centauri, or Proxima of the Centaur, as it passed by. Alpha Centauri A is a yellow dwarf star like our Sun, but it is even bigger than the Sun. 10% more massive, it has a radius 23% larger than our star. It is, as you can see, the brightest star in the triple system. As for Alpha Centauri B, it is an orange dwarf, so it has a smaller size and mass than its companion star, so it is logically less luminous. Alpha Centauri A and B orbit together for 80 years. They are gravitationally bound. The last star of this triple system, Proxima Centauri, has been the closest star to the Sun for 32,000 years. It will remain so for at least that long. But remember that the universe is constantly in motion. Before it, another star was closer to our Sun, and after it, it will be another one. Proxima Centauri is a fascinating star. It is a red dwarf star, not very massive and not very bright. It has a mass 8 times smaller and a radius 6 times smaller than the Sun. Now that it is part of the Alpha Centauri triple system, it has been named Alpha Centauri C by astronomers. Although Proxima Centauri is gravitationally bound to the stellar pair Alpha Centauri AB, you will not see it from Earth, whereas you can distinguish the pair Alpha Centauri AB very well with the naked eye in the southern sky. This seems logical when you know that this star, discovered only in 1915, has a luminosity of only 0.006% of that of the Sun. Proxima Centauri is surrounded by planets, just as our Sun is surrounded by the planets of our solar system. The exoplanet Proxima Centauri B, which orbits Proxima Centauri, is of particular interest to scientists, who call it an exotherm. It is the closest exoplanet to us. Moreover, because it is located in the temperate zone of its star, is rocky, like the Earth, and of a size comparable to our planet, nothing prevents it from being habitable. Furthermore, observations have shown the presence of dust belts containing rock and ice fragments around Proxima Centauri, similar to the asteroid belt and the Kuiper belt in our solar system. This could mean that Proxima Centauri is probably home to more than one planet. While the imaginations of scientists and writers have been fired up about the Alpha Centauri star system, we have not yet been there. Even though Proxima Centauri is the closest star to the Sun, it is still more than 40,000 billion kilometers, or 25,000 billion miles away. The James Webb Telescope itself will not be able to produce images of the surface of stars located so far away, while Proxima Centauri is the closest to us after the Sun. You will tell me that we can send a probe there? Yes, but with current technology, even a probe like Voyager 1 would take more than 70,000 years to reach Alpha Centauri. We will therefore have to wait for the launch of the Future Giant Telescope, ELT, of ESO in Chile, around 2027, to know more about this star system. Unless a project announced in 2016, the Breakthrough Starshot will see the light of day. This project aims to find a way to launch tiny probes weighing only 1 gram into space, propelling them with laser beams to give them more speed. This technique could allow them to reach 20% of the speed of light, or 60,000 kilometers per second, or 37,000 miles per second. These small probes could thus reach the Moon in 7 seconds, and the Alpha Centauri star system in only 20 years. But even if these probes could travel to Alpha Centauri, would their very small size allow them to send back relevant information to Earth? It is true that the question of the return of the information collected by the probes is rather thorny. Even if they were to travel at the speed of light, the information would take 4 years to reach us from Alpha Centauri. Let's continue our journey through space to reach the star Sirius, located 8.6 light-years from Earth, in the constellation of the Great Dog. Sirius A, with its scientific name Alpha Canis Majoris, is the brightest star in our night sky and the 5th closest star to the solar system. You're probably wondering how you can see Sirius so well from Earth without even needing a telescope, while Proxima Centauri, the closest to us after the Sun, is not visible. This is simply because Sirius is a very massive star. It is 1.8 times larger than the Sun, and 2.3 times more massive. Its surface temperature is estimated at more than 9,600 degrees Celsius, or 17,300 degrees Fahrenheit. The star Sirius A has a much smaller companion star, Sirius B. This white dwarf star, which is about the size of the Earth, has a mass equivalent to the Sun. Sirius B was discovered in 1862, a discovery that marks the first in the history of astronomy. It is separated from Sirius A by a distance of about 20 astronomical units, or 20 times the distance between the Earth and the Sun, which is equivalent to the distance between the Sun and Uranus, for example. Its orbit is elliptical and lasts 50 years. The 2 Sirius stars are therefore more or less distant depending on the year. In 2025, it will be the largest possible separation between the 2 stars. Moreover, Sirius A is moving away from us, albeit very slowly. In the 17th century, the astronomer Edmund Halley compared the position of Sirius in the night sky to the position recorded by the astronomer Hipparchus in the 2nd century BC. In 18 centuries, the star has moved about 30 arc minutes, the size of the full moon. It may surprise you that the existence of Sirius was already known in the Hellenistic era. It is even the Greeks who gave it its name. Sirius comes from the Greek Syros, the fiery or burning one. If we look at the history of astronomy, it is not so surprising, because already the Babylonians observed the sky 3,000 years before our era. And Sirius A is so bright that you can't miss it. This star has fascinated people over the centuries. In ancient Egypt, it was associated with the goddess Isis, the wife of Osiris, and one of the 5 children of Nut in the sky, and Geb was the god of the earth. Moreover, the heliacal rising of Sirius, that is to say, the movement when it was the last star to shine before the sunrise, coincided with the summer solstice and the fertile floods of the Nile. It may also be interesting to know that the heliacal rise of Sirius has shifted in time. Indeed, the axis of rotation of the Earth describes a cone in space in 25,800 years. At this moment, the axis of rotation points to the North Star, which is used to indicate the North Pole. but it has not always been so. Over the centuries, this role has been assumed in turn by the star Kochab of the Little Dipper at the time of Homer, and by Thuban, or Alpha of the Dragon, at the time of the construction of the pyramids. In 10,000 years, it will be the star Vega in the constellation of Lyra that will show us north. Before we continue our journey, here are some tips for seeing the star Sirius the next time you look at the stars from Earth. The star Sirius is visible throughout the winter in the constellation of the Great Dog. It can be seen from anywhere on Earth. If you are in the northern hemisphere, the star is part of the winter hexagon. To help you find the brightest star, you can use the 3 stars in Orion's belt, also called the 3 Magi. They point in the direction of Sirius. Just draw a line from these 3 stars. Sirius should not be difficult to spot, since it is much brighter than the others. With a 400mm telescope at least, you can also see the white dwarf Sirius B. One last tip. Sirius is rather low in the sky. The light emitted by the star must therefore cross a great distance of atmosphere to reach us. The turbulence in the atmosphere can produce a flickering effect. That's why sometimes you can get the impression that Sirius is flickering a bit, like an airplane crossing the sky. We are now 35 light-years away from our solar system. The exoplanet in front of you must look familiar. That's normal. It's the closest exoplanet ever photographed in direct view. It is also one of the few exoplanets ever photographed. The picture you have probably already seen was published by a team of researchers from the University of Hawaii on July 6, 2021, in the journal, the Astrophysical Journal Letter. Coconuts 2b is a gas giant like Jupiter. It orbits a star named Coconuts 2a, or L3426. Coconuts 2a is a red dwarf with a mass equivalent to 1/3 of that of the Sun, with a fast rotation period of 2.83 days. The Coconuts 2a star system is quite young and is estimated to be between 150 and 800 million years old, as is the exoplanet Coconuts 2b. For comparison, our Sun is 4.6 billion. It was detected in 2011 by the WISE satellite and then studied through the Coconuts program, which analyzes the characteristics of celestial objects and distant star systems. In 2011, the data received by the WISE satellite suggested that Coconuts 2b was a celestial object drifting in space with no particular orbit. 10 years later, it was concluded that the exoplanet does orbit a star, with an orbital period of more than 1 million years, which is huge. This can be explained by the great distance between this planet and its star, 6,471 astronomical units, which is more than 6,000 times the distance between the Earth and the Sun. Moreover, Coconuts 2b being very far from its star, it is a gaseous planet with an average temperature of 161 degrees Celsius, or 320 degrees Fahrenheit. It makes one revolution around its star, in addition to the one around the Sun. Fortunately for us, this distance allowed us to obtain a direct image of it, without the planet being drowned by the light of its star. Another impressive fact: Coconuts 2b has a mass 6 times greater than that of Jupiter. To give you an idea, Jupiter is already 317 times the mass of the Earth. Coconuts 2b is qualified as an extreme star because of its colossal mass. The extreme stars are all the stars whose characteristics are so singular that they seem inconceivable. Coconuts 2b is thus the second largest exoplanet discovered to date. Let's continue our journey to K2-18, the star system that could host another Earth. We are now 63 light-years from Earth, in the constellation of Pisces. This is where we find the coldest star in the universe, WD 0806-661b. Stars are, by definition, hot bodies. They are made of hot gas, and like a constantly burning engine, they constantly consume energy by emitting heat. The star in front of you holds the record as the coldest star in the universe. It is a brown dwarf star with a surface temperature between 27 and 80 degrees Celsius, or between 80 degrees Fahrenheit and 180 degrees Fahrenheit, temperatures close to those of the Earth. As you can imagine, cold stars are not that common in the universe. The Sun is not the hottest star, and yet its temperature is 6,000 degrees Celsius, or 10,800 degrees Fahrenheit, at its surface, and 15 million degrees Celsius, or 27 million degrees Fahrenheit, at its core. It must be said that brown dwarfs are hardly considered as stars. Their formation is similar to that of a star. That is why they are considered as stars. But they are at the limit between a small cold star and a large hot planet. WD 0806-661b is 6 to 9 times more massive than Jupiter. Categorized as an ultra-cold dwarf because its temperature is below 2,400 degrees Celsius, or 4,350 degrees Fahrenheit, WD 0806-661b, by its mass, is at the limit with the supergiant planets. By definition, a star must have a sufficient mass to trigger the nuclear fusion of hydrogen in its core. The fusion of hydrogen atoms in the core of a star releases a large amount of heat and light, powering the star like a huge engine throughout its life. The minimum mass for this process to occur is about 80 times the mass of Jupiter, or 10% of that of the Sun. Planets do not have a mass large enough to trigger this kind of reaction. But brown dwarfs are very large planets, between 10 and 80 times more massive than Jupiter. They are thus massive enough to allow the fusion of deuterium, also called heavy hydrogen, but not hydrogen. The structure of deuterium facilitates its fusion, despite the relatively low mass of brown dwarfs. Too big to be part of the category of planets, and too small to fit in that of stars, brown dwarfs form a separate category, hence the nickname of failed star. But if brown dwarfs are given a sad nickname, it should not be deduced that their knowledge is of no interest. NASA explains that brown dwarfs could occupy an important part of the mass in the universe. Given that they are not very luminous, it is perhaps towards them that we should turn to finally solve the thorny problem of the missing mass. A mass whose influence is suspected, but that we have not yet managed to detect. Let's continue our journey towards K2-18b. We are now 84 light-years away from Earth. Have you noticed this strange starless planet, which seems to float alone in the universe? It is the exoplanet PSO J318.522. In 2013, an international team of astronomers announced in the journal Astrophysical Journal Letters that they had discovered a lonely world through the Stars 1 telescope, installed near Haleakala in Hawaii. A gaseous exoplanet that orbits no star, Is this even possible? This announcement has shaken the scientific community, because never before has an object floating freely in space been discovered. The mystery is even thicker, as PSO J318.522 has all the characteristics of young planets orbiting other stars: mass, color, and energy. Astronomers have estimated that this strange planet belongs to a collection of stars, the Beta Pictoris moving group, which formed about 12 million years ago. It is therefore very young on the scale of the universe. It is massive, since it is 6 times the mass of Jupiter. It is, however, the lowest mass ever observed for a free-floating body. PSO J318.522 was discovered in 2010, and it is in 2013 that its discovery was confirmed. Astronomers were then studying brown dwarfs, the objects of which we observed a specimen just before. The telescope had been set to detect the faint red glow of brown dwarfs, and it was an exoplanet with a very red spectrum that was discovered. By the way, the spectra of brown dwarfs and gas giants are similar, and the confusion is often made between these two celestial objects. The young planet, PSO J318.522, was observed by a direct observation method. Generally, planets found by direct detection are difficult to study because they are located next to much brighter stars. But since PSO J318.522 is not located near a star, its observation will be facilitated, which can give scientists a lot of information about the internal mechanisms of giant gas planets. Since that discovery, other solitary exoplanets have been found, including CFB-DSIR 2149-0403, which was discovered in 2012 by a team of researchers at the University of Montreal and described as a planetary mass-free object, or brown subdwarf. So how have astronomers explained these wandering planets since these discoveries in the early 2010s? One theory states that these planets would have been ejected from their home systems. There could be smaller planets nearby, such as Earth, that current technologies do not allow us to detect. Let's continue our journey in the universe with another strange exoplanet, TOI 1452b, a super-Earth-like exoplanet that is suspected to be an ocean planet. First of all, it is necessary to understand the term of super-Earth. It designates an exoplanet which has a mass between that of the Earth and that of a giant planet. The mass of a super-Earth is thus between 1 and 5 times the mass of the Earth and 10 times the mass of the Earth. Be careful, a super-Earth is not necessarily a planet that could harbor life. Only the mass is taken into account to qualify an exoplanet as a super-Earth, without taking into account the other conditions necessary to harbor life, such as the presence of water and the composition of the atmosphere, for example. TOI 1452b is a super-Earth located at 100 light-years from Earth in the Dragon constellation. It orbits in the habitable zone of a red dwarf located in a binary system. Its star is therefore smaller than the Sun, which is a yellow dwarf. Spotted by the NASA TESS telescope, TOI 1452b was then observed with powerful instruments. These observations showed that it could be an ocean planet, i.e. a planet covered with a vast and deep layer of water. TOI 1452b has been detected thanks to the transits method, which consists in measuring the light of a star in search of possible decreases of luminosity. A small decrease in brightness at regular intervals is a reliable indication of the presence of an exoplanet orbiting the star, because when the planet passes in front of its star, it occults the star, which causes this decrease in brightness. TOI 1452b passes in front of its star every 11 days. The data collected and analyzed showed that this planet is about 70% larger than the Earth, with a mass of 5 times that of our planet. The solar system of TOI 1452b is said to be binary because it has 2 stars separated by 97 astronomical units, or 2.5 times the distance between the Sun and Pluto. It is around the larger of the 2 stars of this binary system that the ocean planet orbits. An article published in the Astronomical Journal indicates that TOI 1452b is a rocky planet, but with a density less than that of the Earth. The Earth has very little water compared to its mass. Indeed, water represents less than 1% of its mass. Unlike other stars, such as the satellites of Jupiter, Ganymede, and Saturn, Titan and Enceladus, the liquid water on these moons represents from 16 to 46% of the total volume. There is more liquid water inside Europa, Ganymede, and Titan than on Earth. Astronomers are leaning towards the hypothesis that the relatively low density of TOI 1452b is linked to the presence of a lot of water, especially since this planet is neither too close nor too far from its star, which would allow the appearance of water in liquid form. According to estimates, water could constitute 30% of the mass of TOI 1452b, as on the moons Ganymede and Enceladus. There are other exoplanets that are called ocean worlds because of their density, but TOI 1452b is definitely the most interesting because it is relatively close to us. The James Webb Telescope, put into orbit in December 2021, should give even more information on this ocean planet, which is only 100 light-years away from Earth. We will then be able to confirm whether or not TOI 1452b is an ocean planet. It is time for us to leave behind this mysterious planet. We finally arrived in the star system K2-18. It's been a long journey, but you won't regret embarking on this journey in search of the most promising planet for an alien life form. We are 124 light-years from Earth in the constellation Leo. The K2-18 star system you are looking at is also known as EPIC 2019125552. This planetary system is organized around a red dwarf, and it has at least 2 planets, a hot super-Earth called K2-18c, and a smaller, Neptune-like planet called K2-18b. The central star of the K2-18 star system is a red dwarf. Smaller than the Sun, it is about 1/3 of its mass. Its luminosity is only 3% that of the Sun. The surface temperature of this red dwarf is 3,220 degrees Celsius, or 5,800 degrees Fahrenheit, half that of our Sun. It takes about 39 days to make a complete turn on itself, against 25 days for the Sun at the equator, and 36 days at the poles. The star K2-18 is located 124 light-years from Earth, which makes K2-18 a relatively close star system. You surely realized this when you came here. Between the Sun and the red dwarf K2-18, there are only about 15,000 stars. The star K2-18 is very different from the Sun, and not only for reasons of mass, temperature, or rotation on itself. It is a red dwarf, a completely different class of star than the Sun, which is a yellow dwarf. Before continuing to explore the K2-18 star system, let's start by examining this red dwarf. The first red dwarfs were discovered in the 20th century. Proxima Centauri, which we observed earlier, was discovered in 1915, followed by Barnard's star, almost 6 light-years away from our Sun. Red dwarfs are the smallest stars. Their mass is between 8 and 40% of that of the Sun. They are also the most frequent stars. More than 75% of the stars in the Milky Way are red dwarfs, 160 billion out of 300 billion. Moreover, among the 30 nearest stars, 20 are red dwarfs. It is believed that there are billions of super-terrestrial stars orbiting red dwarfs in the Milky Way alone. No red dwarf is visible to the naked eye from Earth, for the simple reason that they are not bright enough. Red dwarfs have, on average, a luminosity equivalent to 1% of that of the Sun. The largest of them can reach 3 to 4% of the Sun's luminosity, not more. Not very massive, red dwarfs are not very hot, and their temperature is always lower than 3,730 degrees Celsius, or 6,700 degrees Fahrenheit. According to astrophysicist models, and given their physical properties, red dwarfs would be likely to shine relatively constantly for hundreds of billions of years, several tens of times the age of the universe. All the red dwarfs that we observe today are only at the beginning of their existence. While some of them, like the red dwarf Proxima of the Centaurus, will shine for more than 1,000 billion years, our Sun will slowly die out in 8 billion years by transforming into a white dwarf. This is enough to make you dizzy. We must not confuse red dwarfs and white dwarfs, which are the corpses of small stars, whose light is extinguished after several billion years. To make it clearer, I will tell you about the Hertzsprung-Russell diagram, which was developed in the early 20th century. The Hertzsprung-Russell diagram classifies stars according to their absolute brightness. This luminosity depends on several factors: the mass of the star and the temperature at the surface. The more massive a star is, the stronger its brightness. Each star does not have a fixed place on this diagram. Remember that the universe and its objects are constantly evolving. The initial mass of the star determines its placement on the diagram, but also its evolution. There are several groups of stars: main sequence stars, white dwarfs, blue giants, red giants, and supergiants. Stars will move from one group to another during their evolution. Let's take the example of the Sun. The Sun is a yellow dwarf. It is currently located in what is called the main sequence of the diagram. The stars of the main sequence are those inside which hydrogen alone is consumed by nuclear reactions. The consumption of hydrogen produces helium, which in large quantities will hinder the nuclear reactions in the heart of the star. When the star has consumed 10 to 20% of its total hydrogen, it will begin to collapse. A nuclear fusion reaction occurs, and the star will swell while cooling. It is at this point, when the drop in temperature results in a red shift, that the Sun will become a red giant. Over billions of years, the star will gradually die out. When the Sun has reached a very low temperature and can only radiate the remaining heat, it will become a white dwarf, the ultimate stage of stellar evolution, before cooling completely, billions of years later, to become a black dwarf. As for red dwarfs, they have a longer lifespan than the Sun. They can consume a larger proportion of hydrogen because the conversion of hydrogen into helium is very slow. In addition, helium does not accumulate in the center of the star, but circulates inside. Red dwarfs will never become red giants because they heat up slowly until all the hydrogen is consumed. Since the Big Bang, there has not been enough time to observe the terminal sequence of a red dwarf. And yet, about 13.8 billion years have passed. The K2-18 star system is home to at least two exoplanets, K2-18b and K2-18c, which orbit the star K2-18. Both are more massive than the Earth. They are rocky superterrestrials, with a mass of 7 and 8.6 times that of the Earth. The closest planet to the star K2-18 is K2-18c. This hot super-Earth was discovered in 2017 and confirmed in 2018. It was in fact by studying K2-18b, which had been discovered earlier in 2015, thanks to the American satellite Kepler, that the researchers spotted the signal of K2-18c and were able to discover this exoplanet. K2-18b is indeed the one that interests astronomers the most. It is the most distant from the star K2-18. It is between 6 and 10 masses of the Earth, and its radius is 2.3 times larger than that of our planet. It has an orbital period of 33 days and an equilibrium temperature of about minus 23 degrees Celsius, or minus 9.4 degrees Fahrenheit, which is very close to the Earth's equilibrium temperatures of minus 18 degrees Celsius, or minus 0.4 degrees Fahrenheit. As a reminder, the equilibrium temperature of a planet is the theoretical temperature of its surface in the absence of an atmosphere. Astronomers believe that K2-18b has all the characteristics to possess liquid water on its surface, which would make it habitable. Its density, however, seems far too low for it to be a rocky planet. Either K2-18b is a rocky planet with liquid water on its surface, or it is a planet covered by a thick layer of ice. In other words, it is a rocky super-Earth, surrounded by a small gaseous envelope, or a gaseous Mini-Neptune, essentially composed of water and covered with ice. In any case, K2-18b is made up largely of so-called volatile constituents, which form a fluid envelope with elements like molecular hydrogen, helium, or water. As often in the observation of the universe, nothing is certain yet. These two hypotheses hold true, and only the observations of the James Webb Telescope can tell us more. Indeed, the telescope is capable of analyzing the atmosphere of exoplanets, as it proved with the exoplanet WASP-39b. I remind you that James Webb has demonstrated the presence of CO2 in the atmosphere of WASP-39b, a hot gaseous planet located 700 light-years away in the Virgo constellation. The principle is quite simple. When the exoplanet passes in front of its star, the light from the star will pass through its atmosphere. Scientists will then be able to study the spectrum of the light, in particular, the absorption lines, which are sort of holes caused by the gases that the light has passed through before reaching us. Each gas has its own absorption lines. Just by studying the spectrum of light from K2-18 passing through the atmosphere of K2-18b, astrophysicists will be able to determine which gases are present and in what proportions in the atmosphere of this exoplanet. In any case, the exoplanet K2-18b is considered by many astronomers as one of the most promising exoplanets for the existence of an extraterrestrial life form, although it is more than 1 billion million kilometers and a half away from Earth. Before diving into the heart of this planet, let's review the criteria that a planet must meet, according to scientists, to be likely to host life. For decades, scientists have limited themselves to our solar system. The search for life on Mars or Venus was the subject of many observations and space explorations. In the 1990s, the question of the existence of extraterrestrial life was revived with the discovery of exoplanets. Exoplanets are, I remind you, planets that orbit other stars than the Sun. They are, in short, all the planets except those of our solar system, namely Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. There are billions of exoplanets in the universe, which are very far from our Earth. The possibility of extraterrestrial life somewhere in the universe is therefore stronger than ever. Since the discovery of exoplanets, scientists have been trying to find another Earth, or at least an exoplanet that would meet all the conditions for the development of life. These criteria were modeled on what we know, the development of life on Earth. For an exoplanet to be a potential candidate for the search for extraterrestrial life, it must first be rocky like the Earth, and not gaseous like Jupiter. It must have water in liquid form on its surface, since water is the basis of life. Why in liquid form? Because liquid water allows molecules to meet and interact to create life. This is not the case with frozen water, for example. Finding an exoplanet that harbors water in liquid form is not so easy. This planet must have a mass close to that of the Earth. If it is too massive, its gravity will attract all the surrounding gases, and we will have a gaseous planet. This is why the most massive planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, are gaseous and not rocky. But if we are in the presence of an exoplanet that is not massive enough, its gravity will be too weak to retain its atmosphere. However, the presence of an atmosphere is another criterion for the development of life. Without an atmosphere, water in liquid form would evaporate instantly. For an exoplanet to harbor water in liquid form, it must also have a moderate surface temperature. This means that it must be neither too hot, otherwise the water would evaporate, nor too cold, otherwise the water would freeze. It must therefore be in what astronomers call the habitable zone of its star, i.e., the zone where the temperature allows the presence of water in liquid form. K2-18b is indeed located in the habitable zone of its star, neither too close nor too far. Earlier in this trip, we talked about its equilibrium temperature, which is minus 23 degrees Celsius, or minus 9.4 degrees Fahrenheit. This is very close to the Earth's equilibrium temperature of -18 degrees Celsius or -0.4 degrees Fahrenheit. In practical terms, K2-18b orbits closer to its star than we do to the Sun. But let's not forget that its star is a red dwarf, smaller and colder than our Sun, which is a yellow dwarf. K2-18b receives about the same amount of energy as we receive from the Sun. According to the analyses, it would receive about 1,500 watts per square meters, while we receive from the Sun 1,370 watts per square meters. However, scientists do not get carried away. It is not because K2-18b is located in the habitable zone of its star that it is necessarily inhabited. The appearance of life on Earth was the result of multiple factors, not only of a favorable temperature. It is possible that K2-18b harbors living single-celled microbes and bacteria, but depending on the composition of its atmosphere, it may not be able to harbor more complex creatures. This has been established for many exoplanets that have been discovered. They were located at the right distance from their star, in the habitable zone, but their atmosphere saturated with toxic gases makes them unsuitable for the emergence of complex life. What convinced scientists that K2-18b could prove interesting for the search for alien life was the discovery of water vapor on this exoplanet in 2019. Two independent studies, combining data from the Kepler, Hubble, and Spitzer telescopes, have concluded that the atmosphere of K2-18b contains significant amounts of water vapor, which is unprecedented for an exoplanet located in the habitable zone of its star. In other words, this is the first exoplanet found that combines being in the habitable zone of its star with evidence in its atmosphere of liquid water. How did scientists discover water vapor in the atmosphere of an exoplanet located more than 100 light-years from our planet? The first team used data from the Hubble telescope's wide field camera and used an algorithm to process the data. They identified the molecular signature of water in the atmosphere of K2-18b. The second team used data acquired during 3 years by the Hubble, Spitzer, and Kepler satellites to analyze 8 transits of K2-18b in front of its star. In particular, they observed the spectra of the starlight passing through the atmosphere of the planet during these 8 transits. They found that the atmosphere of K2-18b is rich in hydrogen and helium, with a high concentration of water vapor, probably between 20% and 50%. According to astrophysicists, detecting water molecules is very common on gas giants like Jupiter, but rarer in the atmosphere of rocky planets like Earth, especially when they are in the habitable zone. Until now, scientists had only deduced from numerical models the presence of water molecules in the atmosphere of Proxima B, which orbits Proxima Centauri, the closest star to the Sun that we observed on our way here earlier. And that's it. The direct detection of water molecules in the atmosphere of the rocky exoplanet K2-18b is thus a new fact, especially since it is quite possible that the detected water could form rain droplets, or even an ocean on the surface of K2-18b. As a reminder, water had already been detected in exoplanets, but they were not in the habitable zone. This is the case, for example, of HD 209458b, WASP 12b, WASP 17b, and WASP 19b. The astrophysicists recalled that the presence of water in the atmosphere of K2-18b does not necessarily mean that it is inhabited or even habitable. Many questions still remain, including how much water vapor is present in the atmosphere, and whether it is accompanied by traces of organic chemistry, such as oxygen and ozone. All that is known is that, like Earth and Venus, K2-18b is probably composed of silicates as a rocky planet, and that water may not be present in liquid form, but as ice. Scientists expect a lot from the observation of K2-18b with the James Webb Space Telescope, launched in December 2021. More powerful than Hubble, it will perhaps be able to tell us more about the precise composition of the atmosphere of K2-18b. If these discoveries have excited a large part of the scientific community, there are still some gray areas. First of all, K2-18b is between 6 and 10 times the mass of the Earth, with a radius of 2.3 that of the Earth. With this radius, its density seems far too low to be a rocky planet. If K2-18b is indeed rocky, then it would be composed largely of so-called volatile constituents, which would form a fluid envelope, such as molecular hydrogen, helium, and water. This is why K2-18b is often referred to as Mini-Neptune. Indeed, Neptune has no solid surface. It is in fact composed of a solid core covered by a warm and dense layer of water and liquid ammonia, and its atmosphere is made of hydrogen and helium. In addition, for water to be present in liquid form on K2-18b, other factors would have to be present. The presence of water molecules in the atmosphere of the exoplanet does not mean that it is present in liquid form. It could very well be in the form of ice. To be sure that the water present on the surface of K2-18b is indeed liquid, it would be necessary to verify the water content of the planet, the composition of the atmosphere, the rotation of the planet, the existence or not of a solid surface. We still don't know if K2-18b looks like a super-Earth or a mini-Neptune, which would be inhospitable. Some scenarios even make it an ocean planet with liquid water under the atmosphere and temperature and pressure conditions close to those of our oceans on Earth. There is one more thing. Is K2-18b really located in the habitable zone of its star? We tend to rely on what we know. So by comparing K2-18b and the Earth, especially their equilibrium temperatures, it seems that yes. But let's not forget that K2-18 is a red dwarf, very different from the Sun, which is a yellow dwarf. The spectrum of K2-18 is more efficient to heat an atmosphere than that of the Sun. If we were to place the Earth at the same location as K2-18b, it is likely that the oceans would evaporate. Instead of reflecting 30% of the incident energy, the Earth would reflect only 10%. For K2-18b to be habitable, it would have to rotate synchronously with its star, i.e., it would always show the same face to K2-18, which would allow thick clouds to form on the exposed half. This would give a habitable climate. These questions are still being studied by astrophysicists, who are waiting for more powerful telescopes like James Webb to confirm or refute their hypotheses. The observations of James Webb could also enlighten us on the difference between methane and water vapor, which remains unclear. Recently, a study conducted by Lesia researchers has shown that the absorption observed by Hubble during the 8 transits of the planet in front of its star could in fact be due to methane. Methane is found in abundance in the atmosphere of temperate mini-Neptunes. Methane is certainly less abundant than water vapor, but the two can be easily confused. The instruments on board James Webb will probably be able to tell us more. Let's assume that K2-18b is indeed home to life. You wonder then what life would be like on this planet located thousands of billions of kilometers away and miles from us. The notion of a habitable zone remains very relative. By definition, it is, as you know, the distance at which a planet, in relation to its star, could potentially harbor liquid water on its surface. The distance varies according to the radiation of the star. For a red dwarf, the zone of habitability is closer than for a yellow dwarf like the Sun, because a red dwarf is colder, smaller, and less luminous than a yellow dwarf. K2-18b is thus located closer to its star than we are to the Sun. Given this proximity, there is a strong chance that K2-18b is in synchronous rotation with its star. On this planet, there would be no nights or seasons. Living beings would be grouped on the day side, the one that is always facing the Sun, while the night side, too cold, would be uninhabited. The red dwarf, as its name indicates, emits a red radiation, unlike our Sun, which emits a yellow radiation. The living beings on K2-18b would thus see in the sky a red star, with a disk certainly larger than the solar disk, since K2-18b is closer to its star than we are to the Sun. The gravity on K2-18b is 37% greater than on Earth. Thus, the development of life on this planet would have adapted to this stronger gravity, giving forms of plants and animals much more imposing than what we can know here on Earth. The living beings would have more strength compared to us, and would need more energy to feed themselves. Obviously, we would not find the same plants on this planet. Studies have shown that plants are indeed sensitive to red light because they have a photoreceptor for red light, a blue-green pigment called phytochrome, which is found in plant cells. Plants grown under red light are larger and taller, with many branches. Red light could also influence the color and flavor of plants. Instead of being green, K2-18b plants would be black in order to better absorb light from the K2-18 star. Red dwarfs are known for their frequent violent eruptions. The Sun also has eruptions, but much less violent than that of red dwarfs. We are also protected by the Earth's magnetic field. On the other hand, the eruptions of red dwarfs would be capable of tearing the atmosphere of the planets around, especially since habitable planets around red dwarfs are much closer to their star than habitable planets around a yellow dwarf like Earth. So even flares similar to those of our Sun could affect planets like K2-18b more. The researchers then wondered if, because of these frequent flares, exoplanets around red dwarfs might be too hostile for the development of life. Not only could a single eruption of the red dwarf K2-18 damage the atmosphere of K2-18b, but also, according to some researchers, there could be a cumulative effect. In other words, the more eruptions there would be, the more the atmosphere would be torn apart. Thus, even the weak eruptions, which seem to be the most frequent, would present a danger. However, it all depends on the composition of the atmosphere, which scientists have not yet been able to determine precisely with respect to K2-18b. It could thus be difficult to find habitable land around red dwarfs. Indeed, a planet of mass equivalent to ours or higher has great chances to keep throughout its evolution because of its gravity, a thick atmosphere. Also, in these conditions where the greenhouse effect is enormous, the possibility that water could remain in a liquid state evaporates. But all is not lost. For researchers, the conditions for a form of life would be more favorable on the surface of worlds less massive than the Earth. Planets similar to Mars, called exomars, which do not retain their atmosphere well, could be good candidates. The good news is that these small balls of rock are probably much more numerous than the larger, more massive planets. If life were possible on K2-18b, the life expectancy of a species could be much greater than that of species on Earth. Because red dwarfs evolve very slowly, much slower than our Sun, which will eventually turn into a red giant, swallowing the Earth in about 5 billion years. A red dwarf, therefore, leaves much more time than a yellow dwarf for life to develop on the planets that orbit it. At the moment, the latest data suggests that water vapor makes up between 0.01% and 50% of the atmosphere of K2-18b. With such a large range, it is difficult to characterize the exoplanet. It could be completely covered with water, or, on the contrary, be a world similar to ours, with lakes and oceans with many exposed lands. What if K2-18b was an ocean planet? If so, the planet would be home to aquatic species, surely different from those found in our oceans. This extraterrestrial ocean could be deep and dense in such a way that even at high temperatures, the pressure would turn the deep water into ice. The immense pressures in these deep ocean regions could lead to the formation of a mantle of exotic ice forms. This ice would not necessarily be as cold as conventional ice. If the planet is close enough to its star, as is the case with K2-18b, and the temperature and pressure at its surface are high enough for the water to reach its boiling point, the water would become a supercritical fluid and would not have a well-defined surface. But according to the latest data, the surface temperature on this planet is between minus 73 degrees Celsius and plus 47 degrees Celsius, i.e., between minus 99.4 degrees Fahrenheit and plus 116.6 degrees Fahrenheit. Even if the temperature is still uncertain, it is not high enough for the water to reach the boiling point. If K2-18b is indeed dominated by water, the atmosphere may be much thicker than Earth's and composed largely of water vapor, producing a very strong greenhouse effect. The problem? Such a planet would have to be small enough not to be able to hold a too thick envelope of hydrogen and helium. Otherwise, they would rather form a hotter version of an ice giant, like Uranus and Neptune, making any form of life impossible. However, K2-18b is a super-Earth and could very well have evolved as a hot Neptune. But its proximity to its central star could save it. Indeed, as K2-18b is close enough to its Sun, it could be stripped of its light elements by the solar flares of the red dwarf, thus preventing the formation of a thick atmosphere. So there could well be stable oceans on K2-18b. Even if the oceans of K2-18b are of different composition than ours, this does not mean that life would be impossible there. On the contrary, it would simply be another form of life. We have found organisms on Earth that are capable of developing in the Dead Sea. The tardigrade is a good example of an ultra-resistant animal species. 1,000 tardigrades were sent to the moon via a space probe in 2019, and since then these animals have survived perfectly well in this inhospitable environment. The tardigrade is an animal with 8 legs, which measures only 1 millimeter, and which can resist to extreme environments. It survives temperatures between -273 degrees Celsius and +340 degrees Celsius, i.e., between -460 degrees Fahrenheit and 644 degrees Fahrenheit. It is 11,000 times more resistant than humankind to X-rays. It survives pressures 4 times higher than the pressure of the deepest part of the ocean, but also the lack of oxygen, dehydration, alcohol, toxic products. In addition, it can reproduce alone. To adapt in this way to such extreme environments, it changes its mode of functioning, and in particular, resorts to cryptobiosis, a state in which it is almost dead. It curls up, it empties itself of its water, which it replaces with a sugar, and it reduces its metabolic process to 0.01% of normal. It can rehydrate and wake up decades later. Outside of cryptobiosis, its lifespan is 1 to 3 years. We could therefore find ultra-resistant animals on K2-18b, whether it is an ocean planet or a rocky planet, which would resist solar flares, and perhaps even the temperatures and lack of luminosity of the night part. The example of the tardigrade shows that we should not underestimate the capacities of animal species. Now, let's suppose that K2-18b could harbor life and that there are aliens on this exoplanet. After all, why not? And if so, could we communicate with them? The participatory project, Stahaya Beyond, which was born in Uzbekistan, aims to send musical tracks to extraterrestrials. The goal is to transform a selection of local and international music into binary code so that it can be sent into space via a UK satellite radio station in order to reach K2-18b, the best candidate to date for the presence of extraterrestrial life. However, although K2-18b is not the most distant exoplanet from us, it would take 124 years for the extraterrestrials to receive the message. The earliest we could get an answer would be 248 years. This project is an opportunity to ask many questions. What will we do if we come into contact with the extraterrestrials? How will we communicate? And especially, how will we understand each other, since they will not speak our language? This also brings us back to the question, are we alone in the universe? A question that astronomers have been asking for centuries, and to which we are not close to finding an answer.